Hello, hello. Hello. Okay. Hi everyone. So good morning all. So first of all, let me know whether audio and video everything is clear. So if you confirm that, we can start the class here. So just let me know whether audio and video everything is clear. Is it clear? Okay. Okay. So I hope you have followed part 1 also, right? So we'll continue wherever we have stopped, right? Okay. So we have started with lossy medium here. Last time we have started this lossy medium, the wave propagation characteristics in a lossy medium. So if you go to one extreme of this lossy medium, it is going to behave as good conducting medium, and if you go to another extreme of this lossy medium, it is going to behave as good dielectric medium. So generally we call this lossy medium also as what? Also as a lossy dielectric. Lossy dielectric. Okay. Okay. So here what are the conditions here? What is the condition for lossy dielectric? Sigma by omega epsilon is lying between what? 0.1 and 10. If this ratio lies between 0.1 and 10, then we will say it as lossy dielectric or lossy medium. So if sigma by omega epsilon ratio, is far greater than 1. So how much greater than 1 here? By default we have considered sigma by omega epsilon ratio. By default we have considered if sigma by omega epsilon ratio greater than or equal to 10, then we can treat the medium as what? Good conducting medium, or we can say the same medium as a high lossy dielectric medium, right? And similarly here, if sigma by omega epsilon ratio is far less than 1, then we can treat that medium as low lossy dielectric or good dielectric medium, right? So in general, if they have not mentioned any condition, then we can take the condition for good dielectric medium as if sigma by omega epsilon ratio is less than or equal to what? 0.1, then we can treat the medium as good dielectric medium, or we can call it as what? We can call it as low lossy dielectric, right? Okay. So if sigma by omega epsilon ratio lies between 0.1 and 10, then we call it as simply lossy dielectric or lossy medium, right? So the two extremes of this lossy dielectric medium is high lossy dielectric and low lossy dielectric. So if they have not mentioned any condition, then we are going to consider this as the condition for high lossy dielectric or good conducting medium, and this as the condition for low lossy dielectric and good dielectric medium, right? So all these things I have already explained in the previous session itself. Okay. So this sigma by omega epsilon ratio, how we got this one? So we got this one by comparing the conduction current densities with respect to what? Displacement current densities. So I have already explained all those things here. So there is no need to again go for all those things, right? We have already completed that one, right? Okay. So since it is a revision session, so based upon the previous questions here, Okay, so whatever the topics that are having the more weightage according to the previous analysis, right? So those topics I will try to cover in this session, right? So what I am saying here is I am going to cover in this session, because why I am saying is if suppose you have not started learning EMT, okay, don't watch this session here. Okay, it is not at all useful. So unnecessarily you are wasting your time. Okay, so if you have left this subject EMT, suppose, so don't watch this session. Okay, you can continue with the other subjects, there is no problem, because it is absolutely a waste of time for you. Okay, instead of that you can revise other subjects, right? So if you have already studied EMT and if you are having some brief knowledge at least, okay, then it will be helpful for you just to revise those things, right? Okay, so that is the suggestion I can give you for the students, right? Okay, next what I am saying here is, so today we are going to cover the main topics is Poynting theorem we are going to cover, right? Okay, so after this Poynting theorem we will start transmission lines here. Okay, so I will explain some main topics of this transmission lines. We try to cover those topics. So then I will try to cover waveguides, right? So here mainly I am going to cover rectangular waveguides, and after this I am going to cover antennas here, antennas. So in antennas also mainly the most weightage in antennas topic is for antenna arrays. So I am going to cover this antenna arrays topic. I will try to cover this antenna arrays topic. Okay, so these are the topics I have planned today, right? Okay, so with this we can complete this revision here, right? So Poynting theorem, transmission lines, waveguides, antenna arrays. So if you are very good, if you are excellent at these topics, so for them also there is no need to watch this session if you are excellent in these topics. Okay, so this session will be useful if you are having at least some brief idea of EMT subject, and if you want to revise those topics again. Okay, so only for those it is going to be helpful, right? Okay, so if you are not studied yet, if you have not started this subject yet, please continue with your subjects only. Don't watch this session here because it is a waste of time, because you are having very less time, right? Okay, okay, so you have to utilize your time effectively in a smart way, right? Okay, okay, right. Okay, so last time we have seen a good conducting medium, right? So good conducting medium last time we have seen. So in good conducting medium we have derived the expression for alpha, and also we have derived the expression for beta. We got the expression for beta, and also we have seen the intrinsic impedance expression for eta, right? So what we got here, square root of omega mu sigma by 2. Here also you are going to get omega mu sigma by 2. So what is intrinsic impedance? We got square root of j omega mu by sigma. So here I have told that the magnitude is nothing but omega mu by sigma and the phase shift is nothing but 45 degrees. So this is the time phase shift between electric field and magnetic field. Yes or no? In case of what? In case of good conducting medium. So these things we have already seen here. And also we have seen the phase velocity in case of what? Good conducting medium. So what is the phase velocity? We got square root of 2 omega by mu sigma. Okay, if you don't remember this formulas also, there is no problem. So phase velocity is nothing but what? Ratio of omega by beta. Understood? So if you take this ratio, you know beta. Okay, if you take the ratio of omega by beta, you are going to get the expression for phase velocity in case of what? Good conducting medium, right? So here we have observed that the phase velocity in case of good conducting medium is depending upon what? Is depending upon frequency. So if it depends upon frequency, then different frequency components are going to travel with different velocities, which is going to cause the distortion. Okay, so that point also I have explained clearly. And one more important point here you have to understand here is, so once we enter into good conducting medium, so always whenever I am saying good conducting medium, you have to remember this condition: sigma by omega epsilon ratio is greater than or equal to 10. That means conduction current densities are 10 times greater than that of displacement current densities. Okay, that's what you have to keep in mind, right? Okay. This is the general condition. Now here I have told that here alpha is proportional to what? Square root of what? Square root of frequency. Here 2 is constant, mu is constant, sigma is constant, omega is nothing but 2 pi f. 2 pi is also constant. So alpha is directly proportional to frequency. So once you attain this condition, then you are going to enter into good conducting medium. Once you enter into good conducting medium, then the attenuation constant in that good conducting medium is directly proportional to what? Frequency. That means in case of good conducting medium, as frequency increases, this attenuation constant is also going to increase. And hence, in a good conducting medium, once you enter into good conducting medium, you have to prefer which type of frequencies here? You have to prefer low frequency signals. Okay, low frequency signals are going to have less attenuation in case of what? This is for good conducting medium. Okay, this is what you have to keep in mind. See here, so the generally I can consider the medium as lossy dielectric, right? So I am saying that sigma by omega epsilon ratio is lying between 0.1 to 10, then we can say it as lossy dielectric. Right. Okay. Now see here. So it is going to become good conducting medium if sigma by omega epsilon ratio is greater than or equal to 10. Right. So and here it becomes good dielectric medium. Sigma by omega epsilon ratio is less than or equal to 0.1. Right. Okay. Fine. So now see here. Now here, as frequency goes on increases here, so generally this lossy dielectric is going to have both conducting nature as well as dielectric nature. Yes or no? So none of these natures are going to dominate here, right? Okay. So here it is going to have both dielectric nature plus what? Plus conducting nature. Both are going to be present, right, in this medium. So now in this medium, let us say sigma of the medium is constant, conductivity of the medium is constant, epsilon is also constant, right? Okay. So what is variable here? What you can vary? You can vary this frequency. Frequency is variable. You can vary the frequency. So as the frequency goes on varies here, if you vary the frequency of the wave, okay, so if you go on increase this frequency, this sigma by omega epsilon ratio tends to what? Tends to 0.1. Yes or no? As this omega value goes on increases, what will happen? This ratio will gradually decrease, and this nature will tends to what? Will tends to 0.1. So that means if it is tending to 0.1, then it is going to act like what? Good dielectric medium. Its behavior is going towards what? Good dielectric medium, or we can say it as what? Low lossy dielectric, right? Okay. Now if suppose omega is decreasing here, so as omega goes on decreases, okay, this ratio will become what? Sigma epsilon are constant for a given medium. So I am just changing the frequency. If omega goes on decreases, then this ratio value is going to increase. So if it goes on increases, then it will approach towards what? It may approach towards 10. Okay, at one stage what will happen? This ratio will become greater than what? Greater than 10. So once it becomes greater than or equal to 10, then the medium is going to behave as what? Then the medium is going to behave as good conducting medium or high lossy dielectric So that means if you are in a lossy dielectric medium, that lossy dielectric medium is going to behave as a good dielectric medium if you go on increase the frequency of the signal. Understood? So if the frequency of the signal goes on increases, then its nature will be tend towards what? Tend towards a good dielectric medium or low lossy dielectric. Understood? And if we want to send the signal here, in a dielectric medium, and hence which frequencies you have to prefer? You have to prefer high frequency signals, because high frequency signals will tend to make the nature of the medium towards what? Towards low lossy dielectric. So for high frequency signals, the same medium is going to behave as what here? Low lossy dielectric. So if it is behaving as low lossy dielectric means you are going to experience low losses, which means the wave can propagate to more distances. Yes or no? That's why in communication, you are going to send the signals through a dielectric medium. Right. Okay. So which frequencies you are going to prefer? You are going to prefer high frequency signals. Yes or no? Why means for high frequency signals, the nature of the medium is tending to low lossy dielectric, right? Okay, okay. So now as the frequency goes on decreases here, as the frequency goes on decreases, then what will happen? You are going to enter into what? You are going to enter into good conducting medium, or we can call it as what? High lossy dielectric. Right. If suppose once you enter into good conducting medium here, once you have entered into good conducting medium, right? Okay. So good conducting medium you have entered means sigma by omega epsilon ratio has become greater than or equal to what? Greater than or equal to 10. So once you entered into this region, then alpha, we have seen that alpha is proportional to square root of frequencies. So in this region, once you have entered in this region, then in this region you have to prefer what? You have to prefer low frequency signals in order to have the less attenuation. Understood? Okay. I hope this point is clear here. Right? Okay? Okay. So these are the things you have to understand. So here so as frequency goes on increases, the nature will tends to good dielectric medium, right? So there exists a minimum frequency, above which the medium is going to behave as what? Good dielectric medium. So if f is greater than this particular minimum frequency, then the medium is going to behave as what? Then the medium is going to behave as good dielectric medium. And similarly, if omega goes on decreases, that means if the frequency goes on decreases, the nature will tend towards what here? Good conducting medium. Understood? So that means there exists a maximum frequency. There exists a maximum frequency below which the medium is going to behave as what? Good conducting medium. So if f is less than what? If f is less than f maximum, then it is going to behave as what? Good conducting medium. So there exists a maximum frequency above which below which the medium is going to behave as what? Good conducting medium. There exists a minimum frequency above which the medium is going to behave as what? Good dielectric medium. So what are the conditions for this minimum frequency and this maximum frequency? Okay, we'll try to get that here. So see here. So here the condition for good dielectric medium is sigma by omega epsilon ratio is less than or equal to what? Less than or equal to 0.1, right? Okay, okay. So now see here sigma by, so here omega is nothing but 2 pi f into epsilon less than or equal to 0.1, right? So now here I am sending this 0.1 to this side. So what you are going to get? You are going to get 10 sigma divided by 2 pi epsilon less than or equal to, I am sending f to this side, so I am going to get f like this. Yes or no? Okay, okay. Yeah. So now if f is greater than or equal to 10 sigma by 2 pi epsilon, okay, if f value is greater than this value, then only it is going to behave as what? Good dielectric medium. So which means there exists a minimum frequency above which the medium is going to behave as a good dielectric medium. So what is that minimum frequency here? That minimum frequency is equivalent to what? 10 sigma by 2 pi epsilon. 10 sigma by 2 pi epsilon, right? Okay, okay. So this is the minimum frequency above which the medium is going to behave as what? Good dielectric medium. These are very, very important here. So because up till now they have not asked any questions based on this condition, so we can expect this type of new questions here, because they won't ask the same questions again and again, right? Okay, they will try to ask some new patterns. Okay, okay. So that's why I am expecting this type of questions they may ask. Okay, okay. So the minimum frequency is equivalent to what? 10 sigma by 2 pi epsilon. So what is the condition for good dielectric medium? If f is greater than f minimum, then it is going to behave as what? Good dielectric medium, right? Okay. Similarly here, so coming to good conducting medium, what is the condition here? What is the condition for good conducting medium? So the condition for good conducting medium is sigma by sigma by omega epsilon ratio must be greater than or equal to what? 10. Okay, so now here now here I can do the same thing, that is sigma by 2 pi f epsilon greater than or equal to 10. So I am sending f to this side, 10 to this side. Okay, so if I send 10 to this side, what you are going to get? Sigma by 20 pi epsilon greater than or equal to f. So that means the condition for a good conducting medium is frequency, the operating frequency must be less than or equal to what? Less than or equal to sigma by 20 pi epsilon. This is the condition for the operating frequency for the medium to behave as what? Good conducting medium, right? Okay, so how we are getting this condition here? By taking this as the condition here, by taking this as the condition. Okay, these are the general and default conditions. If they have given some other condition, you have to follow that condition, right? Okay, okay, yeah. So now see here, f must be less than or equal to what? Sigma by 20 pi epsilon, right? Okay, so from here, what is the maximum frequency that you can have here for the medium to behave as a good conducting medium? What is the maximum frequency you can have? Is nothing but what? Sigma by 20 pi epsilon, sigma by 20 pi epsilon. So this is the maximum frequency you can have, below which the medium is going to behave as what? Good conducting medium. Okay, so f is greater than f maximum, then the medium is going to behave as good conducting medium, or what? Or a high lossy dielectric, high lossy dielectric. And similarly here, if f is what? F is less than, sorry, what I am saying here, sorry, f is less than what? F is less than f maximum, that is the condition for good conducting medium. And here f must be greater than what? F must be greater than f minimum. So this is the condition for good dielectric medium, or what? Or low lossy dielectric. Okay, okay. So I hope we have understood these things in a crystal clear manner. So whenever they have given the problem here, whenever they have given the problem based on these concepts, so first of all, you try to determine sigma by omega epsilon ratio. If they have given the data regarding sigma and frequency and epsilon, then try to determine this sigma by omega epsilon ratio here. So once you determine this sigma by omega epsilon ratio, right, if they have not given any conditions for good conducting medium, for good dielectric medium or lossy dielectric, if they have not given any conditions, then we are going to continue with our conventions here. That is sigma by omega epsilon ratio greater than or equal to 10, it is less than or equal to 0.1, or it is going to lie between 0.1 and 10. We'll follow that conditions. Okay, in this manner, then you can easily solve even 10 problems also. Okay, based on this concept, if they give 10 problems, 10 different types of problems, you can easily solve. Okay, if you do this type of analysis, right? Okay, okay. So for good conducting medium, the intrinsic impedance is nothing but what? Square root of j omega mu by sigma, and phase velocity we got square root of 2 omega by what? Mu sigma, right? And for here alpha lossy, so for lossy dielectric, what we got here? Expression omega into square root of mu epsilon by 2 into square root of 1 plus sigma by omega epsilon whole square minus 1 whole to the power of what? 1 by 2. And here you will get a similar type of expression, but the only thing is here you are having minus, here you are going to get plus. Okay, so into square root of what? 1 plus sigma by omega epsilon whole square plus 1 whole to the power of what? 1 by 2. So for eta lossy, what is the expression we got here? We got a square root of what? J omega mu by sigma plus j omega epsilon. And phase velocity, if you want, you can determine here, that is omega by beta lossy, right? So there is no need to write this as again a formula here. We know already for beta lossy. So you can determine by using this expression, you can determine beta lossy, right? Then after that, you can substitute here. Okay, then you can get the phase velocity for a lossy dielectric medium. Okay, it is as simple as that, right? Okay, okay. So next, for good dielectric medium, I have not derived this one here. Okay, but Here I am not giving the preference for those derivations and all. Okay, so you can just note down. So by using those conditions here, that is the sigma by omega epsilon ratio is far less than 1, that is the condition. So by applying that conditions here, okay, we can get the expressions for alpha, beta, eta and phase velocity, right. So here for alpha you are going to get eta into sigma by 2. So whereas where eta is equal to what? Square root of mu by epsilon, square root of mu by epsilon ohms. Okay, where, so this is the expression you are going to get. So once you enter into good dielectric medium here, once you enter into the region of good dielectric medium or low lossy dielectric medium, you can observe that alpha is independent of what? Frequency, right. Once you entered that threshold region, that is once you entered the frequency greater than what? Minimum frequency, then you are going to enter into good dielectric medium. Once you enter into good dielectric medium, then for all the frequencies, okay, it is going to behave as what? It is going to provide the same attenuation. Understood? Okay, so for a good dielectric medium, anyway, this sigma value is going to be what? This sigma value is going to be negligible here. So it is going to be very small, right? Okay, so if it is very small, then alpha value is also going to be very small in case of what? Good dielectric medium, right? Okay. Okay, so for beta you are going to get approximately, see I have already told that for good dielectric medium the properties are almost similar to that of what? The properties are almost similar to that of lossless medium only. Okay, so since here sigma is very small, it is negligible, so alpha will generally tend to 0 here, right, in case of good dielectric medium. Okay, which is approximately nearer to lossless medium only. Similarly, the expression for beta you are going to get approximately omega into what? Square root of mu epsilon. So all these are approximate relations, right? Okay, and for eta what you are going to get here? So eta is nothing but what? Omega into root over mu epsilon, right? Okay. This is the expression for beta. Next for intrinsic impedance here, so here square root of j omega mu by sigma plus j omega epsilon. So here for good dielectric medium, omega epsilon ratio is far greater than what? Sigma. So if you neglect this one, you are going to get what? For good dielectric medium also you are going to get approximately the relation as a square root of mu by epsilon only. And phase velocity is nothing but what? Omega by beta for good dielectric medium, omega by beta for good dielectric medium. Okay, so you are going to get approximately the same relation, that is 1 by square root of what? Mu epsilon, right? Almost the same relations that you are going to get either for good dielectric medium or lossless medium. Okay. Okay, so first whenever they give the problem, determine sigma by omega epsilon ratio, then you can understand under which region it will come, whether it is good conducting or lossy dielectric or good dielectric. Okay, so based on that you can utilize these formulas here, right? Okay. Okay, so I hope this is crystal clear here. So this type of analysis is equivalent to any type of problem that they can give in this based on this concept here. Okay, if they give 10 problems also you can solve, right? Okay. Okay, so I am giving brief summary, right? Buffering. Is it buffering your video now? Is it buffering or is it clear? Is it clear? Okay. Okay. Right. So I hope it is clear now. Okay. So from my side, don't have any problem here. Everything is clear here. Right. Okay. Right. Okay. So I hope this is crystal clear here. Right. You can do the problem based on this, right? Okay. So now if suppose they have given a problem like this here, that is if suppose they have given gamma propagation constant is equivalent to 3 plus J4, they have given gamma is equivalent to 3 plus J4 meter inverse. So you are having here both alpha as well as what, beta, right? Okay. Okay. So this is what they have given propagation constant, and if they ask you to determine, sigma by omega epsilon ratio here, so that is loss tangent. If suppose they ask to determine loss tangent, that is sigma by omega epsilon ratio. Okay. If suppose they have asked this type of problem. Okay. Sir, previously you have told that if they give sigma by omega epsilon ratio, okay, if they give sigma by omega epsilon ratio, then you can determine all these parameters. Okay. So by deciding whether it is behaving as good conducting or good dielectric or lossy dielectric, based on this, by using these formulas you can solve the problem, right? Okay. But here if you observe here, they are not given conductivity of the medium. They have not mentioned the conductivity of the medium here. They have not given the frequency of the wave, and they have not mentioned epsilon of the medium. They have not mentioned neither epsilon nor omega value nor conductivity value. Okay. They have simply given the propagation constant of the medium, that is they have given alpha value and they have given what, beta value. So in this case, how we can determine the loss tangent? That is a sigma by omega epsilon ratio. How we can determine that? Tell me here. How we can determine that? Tell me. So I think by this time, if you have covered EMT, I hope we have solved all the previous year questions also. Okay. So that's why I am trying to take some new type of problems here. Okay, because in GATE we cannot expect the same type of questions again and again. Okay, so it may happen, and most probably it may not happen also, right? Okay, so that's why I hope you have already familiar with the previous year questions, so that's why I am taking some new questions, right? So if they have asked the question like this, then what is the answer for this one? How you can deal with this type of question? Tell me. So they have given only alpha and beta, they have not given sigma, they have not given omega, they have not given epsilon value. Then how you can determine this sigma by omega epsilon ratio? See here. See, so we don't know the nature of the medium also. So in general we will assume the medium as lossy dielectric. So from lossy dielectric only we are getting the two other extremes. Okay, so here we just assume the medium as lossy dielectric. So for lossy dielectric, what is gamma here? Gamma is equivalent to square root of j omega mu into what? Sigma plus j omega epsilon, right? Okay, gamma is equivalent to square root of j omega mu into what? Sigma plus j omega epsilon, right? Okay, so where this gamma is nothing but what? Alpha plus j beta. So which is equivalent to square root of what? Square root of, okay, square root of j omega mu into what? Okay, okay, j omega mu into sigma plus j omega epsilon. So if you square on both sides here, what you are going to get? alpha square minus beta square plus 2j into alpha beta. So this is equivalent to, so square this one here, what you are going to get, j omega mu into sigma plus j omega epsilon. Okay, so separate real part and imaginary part, what you are going to get, minus omega square mu epsilon plus j omega mu into sigma. Yes or no? Okay, minus omega square mu epsilon plus j omega mu sigma. So this is what you are going to get, alpha square minus beta square plus what, plus j into 2 alpha beta. So if you compare the real parts on both sides and imaginary parts on both sides here, right? Okay, if you compare the real part on both sides, I can write this one as what, beta square minus alpha square is equivalent to what, omega square mu epsilon. Can I write in this manner? Yes or no? By comparing the real parts on both sides, I can write this as what, beta square minus alpha square is equal to omega square mu epsilon. And by comparing the imaginary parts on both sides, I can write it as what, 2 alpha beta is equivalent to what, omega mu sigma. Okay, so from these two expressions, can you get any idea here? So here, if you observe, here we are having a sigma omega mu epsilon, here you are having a omega square mu epsilon. Okay, we want the ratio of what, sigma by omega epsilon. So if you take the ratio of sigma by omega, if you want the ratio of sigma by omega epsilon, what you have to do? So let us consider this as equation 1 and this as equation 2. So if you do 2 by 1 here, if you do 2 by 1, what you are going to get, sigma omega mu divided by omega square mu epsilon, that is nothing but you are going to get sigma by omega epsilon. So which is equivalent to 2 alpha beta divided by what, divided by beta square minus alpha square. Okay, so we can express this sigma by omega epsilon ratio in terms of what, in terms of alpha and beta also, right? So if they simply give the propagation constant like this, if they simply give the propagation constant like this, and if they ask to determine the loss tangent value, so we can express this loss tangent in terms of what, alpha and beta also. So what is the expression for sigma by omega epsilon ratio in terms of alpha and beta here? That is nothing but 2 alpha beta by beta square minus alpha square. So you can remember this as what, you can remember this as a formula here. So if you don't want to remember this as formula, so within 1 or 2 steps, if you know this one, okay, this is the basic equation, if you know this one, you can do within 1 or 2 steps, you can get this relation, right? Okay, okay. So sigma by omega epsilon ratio, that is loss tangent, can also be expressed in terms of alpha and beta. So how it is going to be expressed, that is 2 alpha beta by what, beta square minus alpha square. So in the given problem, they have given alpha value as what, alpha value as 3 and beta value as what, 4. Yes or no? Okay, so alpha value as 3 and beta value as 4. So just substitute this alpha and beta values, then you are going to get this is sigma by omega epsilon ratio. Okay, okay. Yeah. So I hope you can do that one, right? Right. Okay. Yeah. So next, I'll go for skin depth. I'll just briefly explain about skin depth. Okay, so what do you mean by skin depth here? What do you mean by skin depth? So skin depth means, if suppose, see here, let us consider this is z-axis. Okay, so here this medium, this is the interface of the medium, this is the medium I am considering. So let us say this medium is lossy medium. Okay, so in a lossy medium, how the electric field of an electromagnetic wave looks like here? Let us assume the wave is propagating in z direction. So I can represent this as what? It is going to have amplitude. So amplitude is e into e power minus alpha z into what? Into e power j of omega t minus beta z. So in this manner I can represent the electric field of an electromagnetic wave. Okay, so if I consider only amplitude of this wave here, right? So the amplitude is exponentially decaying. It is exponentially decaying in a lossy medium, right? Okay, so as the wave propagates in this medium, as the wave propagates in this lossy medium, what happens to its amplitude here? Its amplitude is going to decay exponentially. So let us consider this is the starting point of the medium. The starting point of the medium I have considered as z is equal to 0. So at z is equal to 0, what is the amplitude you are going to have? You are going to have the peak amplitude, that is nothing but E. Okay, so here at the starting point it is having the peak amplitude, let us say, right? So as the wave propagates in this medium, this amplitude is going to get attenuated exponentially. So it is going to decay exponentially like this, right? So this is nothing but E into e power minus alpha z, right? Okay, so now at this location here, let us say at this location, after traveling this much of distance, right, let us assume the amplitude of the wave has decayed to 1 by E times of its peak amplitude or its initial amplitude. Okay, so at this location, after traveling this location, after traveling this much of distance, at this location, let us say the amplitude has become 1 by E times of its initial amplitude, right? Okay, so the distance up to which the wave has penetrated into this medium before its amplitude decays to what? 1 by E times of its initial amplitude. So this distance we call it as what here? Skin depth. This distance generally we call it as skin depth. Now what is this z value? How much distance it has to travel such that its amplitude is going to decay from E to E by E? So z must be what? At this location, exactly at this location, z must be equivalent to what? Z value must be equivalent to 1 by alpha. So this z is equivalent to 1 by alpha meters is called as what? We can call it as a skin depth. So generally the skin depth is defined as what here? The skin depth is defined as 1 by alpha here, 1 by alpha. Right, so skin depth is nothing but the depth to which an EM wave can penetrate into a medium before its initial amplitude decays to what? 1 by E times of its, before its amplitude decays to what? Decays to 1 by E times of its initial amplitude. Okay, so that distance or that depth, okay, we call it as what here? Skin depth. So the depth to which an EM wave can propagate into a medium before its amplitude decays to 1 by E times of its initial amplitude. So that depth we call it as what here? Skin depth, right? Okay, so now we can define this skin depth for any type of medium. Yes or no? We are having different types of medium. We are having a lossless medium, right? And we are having a lossy dielectric, right? And we are having a high lossy dielectric and low lossy dielectric. So high lossy dielectric are good conducting medium, low lossy dielectric are good dielectric medium. So for all this we are having what? Alpha, right? Skin depth is defined as what here? Skin depth is nothing but delta is equivalent to 1 by alpha. So what is alpha for lossless medium? Alpha value is equivalent to 0. What is alpha for lossy dielectric? Alpha is equal to omega into square root of mu epsilon by 2 into square root of 1 plus sigma by omega epsilon whole square minus 1 whole to the power of 1 by 2, right? So here delta is equal to what? 1 by alpha, okay, for lossy dielectric, this is for lossy, right? Okay, and what is the skin depth for a high lossy dielectric medium or good conducting medium here? So skin depth here, alpha is equal to what? Square root of omega mu sigma by 2, right? So this is for a good conducting medium. So skin depth in case of a good conducting medium is equivalent to what? 1 by alpha, right? Just substitute this alpha values, that's it. There is no need to remember the formula again. If you know alpha values for all the medium, then you can determine delta value, right? So for a good dielectric medium, what is alpha we got? For good dielectric medium, alpha is eta into sigma by 2, right? So you can determine for good dielectric medium is equivalent to 1 by alpha for good dielectric medium, right? So you can define skin depth for any type of medium here, for any type of medium. So generally the skin depth is nothing but what? 1 by alpha, You remember this as simply 1 by alpha for any medium here, right? Okay, so in general for a lossless medium, delta is equivalent to what? Delta is equivalent to infinity, right? Why means in a lossless medium, as the wave propagates, it is not going to undergo the attenuation. It is not going to undergo the attenuation. Okay, it simply travels in the medium without any attenuation. So it will take infinite distance in order to attenuate to 1 by e times of its initial amplitude. Understood? Okay, so which means it will never attenuate, right? So that's why skin depth is equivalent to what? Infinite meters. Infinite. This is infinite, right? So here you can substitute this alpha formula here, then you are going to get the skin depth for what? For lossy dielectric. And if you substitute this alpha value here, you are going to get for good conducting medium. And if you substitute alpha value here, you are going to get for good dielectric medium. But in general here, if they have not mentioned, okay, whether it is lossless or lossy or high lossy or low lossy, and they have not given any clue to determine sigma by omega epsilon ratio. See, if you know sigma by omega epsilon ratio, then you can judge the type of medium, right? So if they have not given any clue to judge the type of medium, and if they simply asking about skin depth, then by default you have to consider the skin depth for what here? You have to consider the skin depth for a good conducting medium. Okay, so actually speaking, they have to mention each and everything in detail in the question, but unfortunately they are not mentioning each and everything about in the question here. So they, in some questions they will ask directly the skin depth. Okay, so whenever they are asking the skin depth directly, then by default you have to consider what? You have to consider this high lossy dielectric medium or good conducting medium. Okay, so this is what you have to consider by default. By default, if they have not given any clue, and if they are simply talking about the skin depth, then by default you have to consider the skin depth for what? The skin depth for good conducting medium or high lossy dielectric, right? Okay, if they give sigma by omega epsilon ratio, or if they have given any clue to determine the nature of the medium, then it is well and good. Okay, it is crystal clear which one you have to choose. But if they have not mentioned, and if they have not given any clue to determine the nature of the medium, and if they are simply talking about the skin depth, then by default you have to assume the medium as what here? Good conducting medium. Understood? Okay, okay, right? Right. So we will solve one problem here based on this. So let us say I am taking sea water. Let us take sea water. So for sea water, I am mentioning the properties of the sea water here. So sigma is equivalent to let us say 10 to the power of minus 4 mho per meter. That is the conductivity. Next mu r is equivalent to 1. Let us say epsilon r is equivalent to 81, right? Okay, so these are the parameters I have given for sea water, right? Okay, so the first question I am asking here is maximum frequency. You have to determine maximum frequency below which sea water behaves as what? Behaves as a good conducting medium. This is the first question. And the second one is if f is equal to okay. So first we try to determine this one here. After that I will frame the second question, right? Okay. So see here, for sea water, what they have given? They have given the conductivity as 10 to the power of minus 4 mho per meter. Epsilon r is equivalent to 80 or 81. What I have given? 81, right? So epsilon r is equal to 81. Next mu r equal to 1. These are the parameters I have given. Okay. Okay. So you have to determine the maximum frequency. You have to determine the maximum frequency below which the seawater is going to behave as good conducting medium, right? Okay. So what is the condition for the maximum frequency below which the medium is going to behave as good conducting medium here? Just now I have told, so that is F maximum is equivalent to what? Is equivalent to sigma by what? F maximum is equivalent to what we got here. So here we have determined F maximum is equivalent to what? Sigma by 20 pi epsilon. Sigma by 20 pi epsilon, right? F maximum is equivalent to sigma by what? Sigma by 20 pi epsilon. This is the maximum frequency below which the medium is going to behave as good conducting medium. So conductivity they have given as 10 to the power of minus 4 divided by what? 20 pi. Epsilon value is epsilon naught into epsilon r. Epsilon naught value is 1 by 36 pi into 10 to the power of minus 9. Epsilon r value is 81, right? Okay. So from here you can easily determine here. So here pi will get cancelled, and here 2 tens and here 2 18s. So here 9 2s and here 9 9s, right? Okay. Okay. So here what you are going to get? So here 10 and here 10 power minus 9. So that means here you are having 10 power minus 8. Okay. Okay. So I am taking 2 to the numerator. So 2 divided by 9 into 10 to the power of minus 4 into what? If I take this 10 power minus 8 to the numerator, you are going to get 10 power 8. Okay. So if you do this, you are going to get 2 by 9 into what? Into 10 to the power of 4 here. So 2 by 9, what is this 2 by 9 here? So 9 ones are 9 point, so 9 twos are 18, 9 twos are 18. So it will go on, right? So 0.22 into 10 to the power of 4. This is this is greater than what? This is greater than 10. Yes or no? This is greater than 10. Oh, wait. Yes. Yes. Sorry, what we have to determine? Maximum frequency, na? Sorry. So what is the maximum frequency we got here? We got 0.22 into 10 to the power of 4, right? Correct now? Okay, you can check the calculation here. So sorry, I am calculating the frequency now. So F maximum is equivalent to what? Is equivalent to 0.22 into 10 power 4, that is 2.2 kilohertz. Okay, so this is the maximum frequency here. So you can do the calculation here, right? So calculation is, I think I have done correctly. So if there are any mistake in calculation, you have to adjust that, right? Okay, but if you understand the procedure, then that is more than enough, right? Okay. Right. Okay. So this is the maximum frequency below which the medium is going to behave as what? Good conducting medium. Right. Now, if suppose in the same question, if they have asked like at F is equivalent to some 10 kilohertz. If F is equivalent to 10 kilohertz, or if they given F is equivalent to some 1 kilohertz here. F is equivalent to 1 kilohertz. So at this frequency they have asked to determine skin depth, and let us say third question they have given at frequency F is equivalent to 10 kilohertz. Okay, they have asked to determine the skin depth, right? And let us say at frequency F is equivalent to 10 megahertz. f is equivalent to 10 megahertz if they ask to determine the skin depth. Okay, so how you can determine the skin depth here for this problem? So here f maximum is 2.2 kilohertz. So that means f less than f maximum, f less than f maximum is going to behave as what? Good conducting medium, good conducting medium, right? Okay, okay. So here if you consider 1 kilohertz here, 1 kilohertz is less than what? If you observe here, f less than what? F less than f maximum, right? So which means here the medium is going to behave as what? For this frequency, the medium is going to behave as good conducting medium. So in this case, if they ask to determine the skin depth, so you have to determine the skin depth for what? For good conducting medium, that is 1 by alpha for good conducting medium, right? Okay, so if you substitute alpha value here, that is 1 by square root of omega mu sigma by 2, so you are going to get the expression as, okay, so if you simplify this, you are going to get the expression as 1 by square root of pi f mu sigma, right? So this is what you are going to get here, right? So now you know f value 1 kilohertz, so pi mu is nothing but mu naught into mu r value is 1, you know mu naught value. So sigma value they have given as 10 power minus 4. So by substituting those values, you can determine what? You can determine this skin depth, right? Okay, okay. So similarly they have given f is equal to what? 10 kilohertz. So at f is equal to 10 kilohertz, how it is going to behave as, how the medium is behaving as, that's what you have to check. So for this, what you have to do, you have to determine sigma by omega epsilon ratio. So sigma is nothing but 10 to the power of minus 4 and omega is nothing but 2 pi into f. F value is 10 kilohertz, that is 10 to the power of 4. Epsilon value is epsilon naught into epsilon r, that is 1 by 36 pi. 1 by 36 pi into what? Into 10 to the power of minus 9 into epsilon r. Epsilon r value is 81, right? Okay. So if you do this, what you are going to get? Here 10 power 4 and here 10 power minus 4 will get cancelled. So here 10 power minus 5 will be left out. So here 2 pi 1s and here 2 pi 18s. So here 9 2s and here 9 9s. Okay, so what you are going to get? You are going to get 9 by 2 into what? 10 to the power of minus 4 into what? 10 to the power of 5. Okay, so 9 by 2 is nothing but what? Sorry, 9 by 2 or 2 by 9? 2 by 9, right? Sorry. So here you are going to get 2 by 9, right? So 2 by 9 into what? 10 power minus 4 into 10 power 5. So here 10 power minus 4, here 10 power 4 will get cancelled. So you are going to get 20 by 9. Okay, so 20 by 9, what is 20 by 9 here? So 9 1s, 9 2s are 18, right? So point, again 2 will be left out, 9 2s are 18, so 2.2222 and so on. So that means here sigma by omega epsilon ratio, here what we got? Sigma by omega epsilon ratio is equivalent to what? Is equivalent to 2.22, which means here sigma by omega epsilon ratio is lying between what? 0.1 and 10. So here the medium is behaving as what? For this frequency, the medium is behaving as lossy dielectric. So here you have to use the skin depth for what? Lossy dielectric, that is delta is equal to what? Delta is equal to 1 by alpha lossy. Okay, you know this expression here, you know this expression. So you have to just substitute the expression for alpha lossy here, and thus you have to determine the skin depth, right? Okay, similarly they have given the frequency at 10 megahertz. They have given the frequency as 10 megahertz. So at this frequency, you have to determine what? Sigma by omega epsilon ratio. Okay, so what you are going to get here? So sigma is nothing but 10 power minus 4. There is no need to calculate again and again here. You have already determined this is sigma by epsilon. Sigma by epsilon, you know. Okay, 2 pi. 2 pi will be same, epsilon value is going to be same. What is going to change? Only frequency. Here f is equal to 10 kilohertz, here f is equal to 10 megahertz. So here instead of 10 power 4, you have to place what? You have to place 10 to the power of 7. Yes or no? 10 to the power of 7. So if you place here 10 to the power of 7, okay, here 10 power minus 9 is present. So 10 power 7, 10 power minus 7 will get cancelled. So here you are going to get 10 power minus 2. right? Okay, so 10 power minus 2. So if you take this 10 power minus 2, right, 10 power minus 2 to the numerator, what you are going to get? 10 power 2. So 10 power 2 into 10 power minus 4 is nothing but 10 power minus 2. So you are going to get here 2 by 9 into what? 10 to the power of minus 2, right? Okay, so we can guess that this value is what? This value is less than what? Less than 0.1 only. So that means the medium is going to behave as what? This is the sigma by omega epsilon ratio we got. This value is going to be less than 0.1. We can easily guess that. Okay, so from here we can judge the medium as what? Good dielectric medium. So here if they ask to determine the skin depth, you have to determine the skin depth as 1 by what? 1 by alpha. So this alpha is for what? Good dielectric medium, right? So where alpha is equal to what? Here where alpha is equivalent to sigma by 2 into eta, right? Okay, so this is the expression where this eta is nothing but square root of mu by epsilon. Right, so in this manner you have to solve the problem here, right? Okay, so I hope these problems are crystal clear, right? Is it clear here? Tell me. Is this clear? Tell me here, is this clear? Yes? So if it is clear, then we will move on to next topic. Tell me here, is this problem clear? Right? Okay. So next we will see the next topic, that is Poynting theorem. Okay, so Poynting theorem. So in Poynting theorem, okay, so mostly we can expect the questions from time average Poynting vector here. We can expect the questions from time average Poynting vector. Time average Poynting vector. Okay, see here. See the Poynting vector, we can represent Poynting vector here. I will explain the difference between Poynting vector and time average Poynting vector. So Poynting vector is nothing but E bar cross what? E bar cross H bar. So you have to always keep in mind that this E bar is the electric field of an electromagnetic wave and this H bar is the magnetic field of an electromagnetic wave, right? So E and H are the electric and magnetic fields of an electromagnetic wave, right? So if you do E bar cross H bar, then we call it as what here? Poynting vector. So this Poynting vector, the resultant of E bar cross H bar is nothing but a vector quantity, and that vector is always going to point along the direction of what? Along the direction of wave propagation. Okay. So here, if you observe here, this electric field is a function of what? Is a function of both space as well as what? Space as well as time, right? Okay. So with respect to time, I have already told that these fields are going to vary time harmonically with respect to time. So time harmonic fields means what here? They are going to vary sinusoidally with respect to time. So with respect to time, this electric field and magnetic field are going to vary sinusoidally. So sinusoidally varying means they are periodic in nature. So if they are periodic in nature, then we can determine its average value. Yes or no here? Okay. So here the electric field and magnetic field are periodic in time. So since they are periodic in time, we can determine its average value. So the average value of this Poynting vector is called as what here? Time average Poynting vector, because we are determining the average with respect to what? With respect to time. Okay. So how you can determine the time average Poynting vector here? So this is in general, we are going to represent this Poynting vector either with what? Either with S bar, or we can represent with P bar. Okay. In some books they will represent with P bar, and in some books they will represent with S bar, but I am going to follow this convention, that is S bar. Okay. Poynting vector. So if you want to determine the time average Poynting vector here, time average Poynting vector, time average Poynting vector. So that is nothing but S average. So here we are calculating the average with respect to time. So that is equivalent to what? That is equivalent to. So here this S bar, since E bar and H bar are functions of time, this S bar will also become functions of time only. So and it is periodic in nature. So how you can determine the average value for a periodic signal here? What you have to do? You have to integrate this signal. Over its time period and divide that with its time period. Then you are going to get the time average. So that is nothing but first you have to integrate this S bar of t. Okay. So S bar of t with respect to what? With respect to time. And you have to divide this whole thing with what? With its time period. Then you are going to get what? You are going to get the time average Poynting vector. So this is nothing but 1 by t into integral 0 to t E bar cross what? E bar cross H bar into what? Into dt. Right? Okay. So here we know how the fields are going to, how we can represent the fields of an electromagnetic wave. So we know how to represent the electric field of an electromagnetic wave, and we know how to represent the magnetic field of an electromagnetic wave. So you can consider the real time expressions for electric field, that is E bar is equivalent to, let us assume the electric field is having x component, let us assume here. So if you assume x component, then I can represent it as Ex into cos of what? Cos of omega t minus beta z. I am assuming it as an x component. Then the magnetic field must lie in which direction here? It has to lie in y direction. Yes or no? Since the wave is propagating in positive z direction, H field must lie in y direction here. So Hy of cos of omega t minus beta z into what? Into ay cap. So since in generally we are considering the medium as what? The medium as lossy medium, the amplitudes has to decay exponentially, that is Ex into e power minus alpha z, here Hy into e power minus alpha z. And in case of lossy medium, right, there must exist some time phase shift between electric field and magnetic field. So that time phase shift between electric field and magnetic field I am considering as what? I am considering as phi. So this phi is the time phase shift between electric field and magnetic field. Okay. So just by substituting this in this expression and doing some mathematical simplifications, then you are going to get the expression for what? Time average Poynting vector. Okay. So what is the expression you are going to get here for time average Poynting vector? So the time average Poynting vector you are going to get, see, for this if I consider the x component of electric field, So correspondingly you are going to have y component of magnetic field, and the wave is propagating. Here I have assumed that the wave is propagating in positive z direction, right? Okay. Okay, so for this case, the time average Poynting vector you are going to get as what here, half into Ex square, divided by what? Divided by, so here you have to write a magnitude of what? Eta lossy. Magnitude of eta lossy into e power minus 2 alpha z into what? Into cos of phi. So this phi is the time phase shift between electric field and magnetic field. Okay, and always this time average Poynting vector is going to point along the direction of wave propagation. So here we have assumed that the wave is propagating in positive z direction. So this time average Poynting vector has to point along the direction of wave propagation, that is along az cap, right? Okay, so here the units of electric field is nothing but volt per meter, and the units of magnetic field is nothing but what? Ampere per meter, and the units of this time average Poynting vector is nothing but what? Watt per meter square. Understood? Okay. Okay, so I can generalize the formula here. Now I can generalize the formula here. So like if suppose similarly if you consider the y component of electric field here, let us assume you have considered the y component of electric field in the same manner, Ey into e power minus alpha z into cos of omega t minus beta z plus phi into ay cap. Suppose you have considered y component of electric field, then you would have get here half into Ey square by magnitude of eta lossy, and the same expression you are going to get. So if suppose if the electric field is having both x component as well as what? Y component, then what is the expression you are going to get here for time average Poynting vector? Then for time average Poynting vector you are going to get the expression as what? Now you are having both x component as well as y component, so you are going to get Ex square plus what? Ey square divided by what? Divided by magnitude of what? Eta lossy into e power minus 2 alpha z into what? Into cos phi. So the wave is propagating, let us assume we have assumed the wave is propagating in az cap direction. Okay. Okay, so general expression here, how I can generalize this one is S average is equivalent to half into, so this is Ex square plus Ey square, so it is just like a magnitude of what? Magnitude of E bar square, which is having x component and y component. So I can write this as half into what? Half into E square, right? Half into simply E square divided by what? Divided by magnitude of what? Magnitude of eta lossy into what? E power minus 2 alpha z into what? Into cos phi. So here I can represent AP cap, where AP cap is the unit vector along the propagation direction, right? Okay, so in this manner I can generally represent the expression for time average Poynting vector. So if you want to represent in terms of H field here, so we know the relation between electric field and magnetic field, that is E by H is equivalent to what? H is equivalent to eta, right? So if you consider the medium as lossy medium, then here this will become eta lossy, right? Okay. Okay, so in this case how you can write here? How you can write in terms of magnetic field? So electric field is equivalent to what? Eta lossy. Consider only magnitudes here. Okay. Okay. So eta lossy into what? Into H field, right? So in place of E you can replace with eta lossy into H. Then what you are going to get? You are going to get the expression as, in terms of magnetic field, you are going to get half into eta lossy into what? Magnitude of H square into e power minus 2 alpha z into what? Cos phi. Okay, cos phi into what? AP cap. So since we are assuming here the wave is propagating in z direction, so here this AP cap is nothing but what? This AP cap is nothing but AZ cap. Okay. Okay. Since I am assuming the wave is propagating in z direction here, that's why it is decaying exponentially along z direction, right? Okay. Okay. Right. Okay. So If suppose they have given the medium as a lossless medium. So in case of lossless medium, what are the changes that are going to take place here? We know that in a lossless medium, there exists no time phase shift between electric field and magnetic field. So here phi represents the time phase shift between electric field and magnetic field. In case of lossless medium, there exists no time phase shift between electric field and magnetic field. That is, phi value must become equivalent to 0 in case of lossless medium. So just substitute phi is equal to 0. And also we know that in case of lossless medium, there will be no attenuation at all, which means alpha must also be equivalent to 0 in case of lossless medium. Okay, so if you put just what is the condition you have to put? You have to put alpha is equal to 0 and phi is equal to what? Phi is equal to 0. If you substitute this, you are going to get the expressions for time average Poynting vector in case of what? Lossless medium. So what are the expressions you are going to get? It is very simple here. That is, S average is equivalent to what? Half into E square divided by what? Divided by eta. Okay, alpha is 0. So that means this term will be become 1. Right? Eta lossy will become what? Eta for lossless medium. Right? And phi is equal to 0. That is, cos 0 is 1. Right? So you will get simple expression like this, half into E square by eta. So here you have to represent the direction of wave propagation here. Understood? Okay, or you can represent in terms of magnetic field, you can represent it as eta into what? Half into eta into magnitude of h square into what? Into AP cap. So in this manner also you can represent. This is for lossless medium. Right? Okay. Right. So this is the time average Poynting vector. Right. Okay. So they have given a problem here. I will take one simple problem here based on this. Right. Okay. So that is in free space, they have mentioned the medium as what? Free space. So free space means you have to keep in mind that free space means it represents what? Lossless medium. Right? Okay. So in free space, they have given H field. They have given H bar is equivalent to okay, some okay. Wait here 1 minute, I will take that problem. Okay. So they have given H field is equivalent to 5√3 by eta naught into cos of omega t minus beta z ax cap plus 5 by eta naught into sine of omega t minus beta z into what? Into ay cap. Right. So this is the H field they have given, and they have asked us to determine what? To determine the time average Poynting vector. Okay, this is the question they have given. So what is the medium they have given? The medium is nothing but free space, and in that medium they have given the magnetic field of an electromagnetic wave, and they have asked to determine the time average Poynting vector. Okay, so if you observe here, for H field what they have given? They have given the x component of H field, and also they have given the y component of H field, and here the wave is propagating in which direction? Wave is propagating in positive z direction. The wave is propagating in positive z direction. So the amplitude, the peak amplitude of this x component I am representing as what? Hx, and this peak amplitude of y component I am representing as what? Hy. Right? Okay. So now they are asking us to determine what? Time average Poynting vector. Right? So what is time average Poynting vector here? So this is a free space here they have given. Free space means it represents what? It represents a lossless medium. lossless medium. It represents lossless medium. So for a lossless medium, what is the time average Poynting vector? So time average Poynting vector in terms of H field, what is that? Half into. So since it is free space, okay, so since it is free space, eta will become eta naught. So eta naught into what? Into H square. But here you are having two components of H field here. One is X component and another one is what? Y component. Right. So with respect to X component, what you are going to get? Hx square. Yes or no? Half into eta naught into what? Into Hx square. This is what you will get if you are having only X component. And if you are having only Y component, what you would have got? Half into eta naught into Hy square. Okay. Now you are having both X component as well as Y component. So you will get Hx square plus what? Plus Hy square. So e power minus 2 alpha z, alpha equal to 0, cos phi, phi is equal to 0 in case of what? In case of lossless medium. Okay, and since the wave is propagating in positive z direction, so Poynting vector has to always point along the direction of wave propagation. So its direction must be what? Must be az cap. Right? Okay, so now you can easily substitute these values here. Half into eta naught into Hx. Hx is nothing but 5 root 3 by eta naught whole square plus Hy is nothing but 5 by eta naught whole square into what? Into az cap. So if you do this, what you are going to get? Half into eta naught. So 25 into 3, that is 75 plus 25 divided by eta naught square az cap. Right. So here this eta naught will get cancelled. You are going to get what? 50 by eta naught into what? Az cap watt per meter square. Right. So this is the time average Poynting vector you are going to get. Right. Okay. So now they can frame different types of problems here. Like they may give you some lossy medium. So if they give lossy medium, what are the extra things that you are going to get? You are going to get e power minus 2 alpha z term and you are going to get cos phi term. Remaining everything is going to be same. Okay, so that's what you have to take care of. Right. So they may give you the clue regarding the medium. That means they may give you sigma value and they may give you omega value and they may give you epsilon value. So based on this sigma by omega epsilon ratio, you can judge the nature of the medium. So once you judge the nature of the medium, then accordingly for that medium you can determine the intrinsic impedance. So depending upon the sigma by omega epsilon ratio, you have to judge the type of medium, and for that particular type of medium you have to determine the intrinsic impedance value. So once you determine the intrinsic impedance value, okay, then if they have given any clue to determine what? To determine alpha. For this particular medium you have to determine alpha, and for this particular medium you have to determine the time phase shift between electric field and magnetic field. So in general most of the cases they will give this time phase shift. Okay, or if you determine intrinsic impedance here, so it is going to have in general let us assume you are getting a lossy medium. For lossy medium, eta is complex quantity, so you are going to have magnitude as well as phase shift. So that phase shift is nothing but phi. So you can determine phase shift phi from this expression itself. Okay, and also they will give some clue to determine what? To determine alpha, or they may give directly alpha value also. Right. Okay, so from that you can determine alpha value. So if you know eta, if you know alpha, if you know phi, then you can determine what? The time average Poynting vector or not. Okay, anyway they will give the expression for electric field or magnetic field in that particular medium, right? Okay, yeah. So from that you can get the peak amplitudes of electric field or magnetic field. So once you know the peak amplitudes of electric field or magnetic field, okay, and if you know alpha value and if you determine eta, okay, here remember that you have to write only magnitude of eta here. Okay, and here you have to write what? Here you have to write the time phase shift between electric field and magnetic field. So if you assume the medium as lossy medium, then eta lossy is going to have magnitude of eta lossy, and it is going to have some phase shift. Okay, so this phase shift you have to write here, and the magnitude, this magnitude you have to write here, right? And from the given expression you can determine what? You can determine this peak amplitude magnitude square, right? And from the given expression you can determine this alpha value, okay, or they may give directly in the expression this alpha value also, right? Okay. So in this manner they can frame different types of problems based on this here, by linking the nature of the medium and this Poynting theorem. They may give the questions like this, right? Okay. Right. Next. Okay, so I hope you can solve this type of problems. Next, see here, if suppose, so here this time average Poynting vector, the units of this one is nothing but what? Watt per meter square, right? So that means it represents the power that is penetrating per unit area. So this represents what here? This represents power penetrating per what? Per unit area, right? Okay. So now if suppose I have considered some closed surface here, right? So here you are having some source of electromagnetic energy. Here. Okay, so let us assume this electromagnetic energy is leaving this closed surface. Okay, so that means the electromagnetic power, I can say the power is leaving this closed surface. The electromagnetic energy that is leaving per unit time is called as what? Is called as electromagnetic power. You can say it as power. Okay, so let us assume the power that is penetrating per unit area. So if I consider some unit area here, so let us assume the power that is penetrating per unit area, they have given as what? S average, right? Okay, so now if you want to determine the power that is penetrating throughout this closed surface here, then how you can determine that? So what you can do here is you consider a small differential area here. Okay, you consider a small differential area dA bar. Okay, so first try to determine the power that is penetrating through this small differential area dA bar. See, the power penetrating per unit area is nothing but S average. The power penetrating through small differential area dA bar, I can represent it as what? S average dot what? Dot dA bar. So this represents the power penetrating through small differential area dA bar. Yes or no? Now if you want to determine the power that is penetrating throughout this closed surface, then what you have to do? You have to integrate this throughout what? Throughout this closed surface. So this represents closed surface integral S bar average dot dA bar will represent what? Will represent the average power. The average power that is leaving, the total average power that is leaving this closed surface. Yes or no? So this represents a total average power here, total average power that is leaving what? That is leaving the closed surface, Okay, yeah. If suppose if I consider a open surface like this, let us assume this is the surface I have considered. Okay, let us assume the time average Poynting vector is in this direction, S average is in this direction, right? So in this case, how you can determine, let us say this total area is A bar. So if you want to determine the time average Poynting, the total time average power that is penetrating through this surface here. Now here this surface is nothing but what? Simply open surface. So in this case, how you can represent the power that is penetrating through this surface is nothing but what? So in the same manner here, you can consider what? A small differential area dA bar. The power penetrating through this small differential area dA bar is nothing but what? S average dot what? dA bar. If you want the total power throughout this surface, what you have to do? You have to integrate throughout this surface. Okay, so this is the total average power that is penetrating through this given surface, right? So here the surface is open surface and here the surface is what? Closed surface. That is the only difference. So if it is closed surface, you have to do the integration throughout that closed surface. If it is open surface, you have to do the integration throughout this open surface, right? Okay, okay, yeah. So this represents a total average power through the given surface here, right? Okay, okay, right. So generally the total average power through a given surface, you can represent it as what? You can represent it as double integral S bar average dot what? Dot dA bar. So if they have given particularly closed surface, then you have to put here closed surface integration. That's it. Okay, okay, right. So this is the general representation, right? Okay. So now see here, if they have given the problem like in free space, they have given the medium as free space, right? Okay, the electric field they have given E bar is equivalent to, so let us take a E bar is equivalent to okay, so E bar is equivalent to 24 pi into what? Cos of omega t minus beta x, omega t minus beta x ay cap volt per meter. Okay, so this is the electric field they have given in free space here, in free space, right? Okay, okay. And they have given that consider a square area, of 10 centimeter into 10 centimeter on a surface whose equation is given by x plus y is equivalent to 1. Consider a square area of 10 centimeter by 10 centimeter on a surface whose equation is given by what? That surface equation they have given as what? X plus y is equal to 1. So this is the surface they have given. Okay, so then determine power flow, that is determine average power flow. See, if they simply give power flow also, you have to understand that it is average power flow. Okay, so determine average power flow through the given squared area, Okay, so this is the question they are asking here. What is the question? So in free space they have given the medium as what here? Free space. Okay, free space means the intrinsic impedance is nothing but what? Eta naught, which is equivalent to 125 ohm or 377 ohm. Okay, so in this medium they have given the electric field as 24 pi into cos of omega t minus beta x. So the electric field is pointing in which direction? Plus ay cap direction, and the wave is propagating in which direction? Positive x direction. Wave is propagating in positive x direction, right? And the electric field is pointing in positive y direction, right? This is what we can observe, right? And they are saying that consider a square area of 10 centimeter into 10 centimeter. That means the magnitude of area here, the magnitude of area they have given as what? 100 centimeter square. 10 into 10 is nothing but 100. So the magnitude of area they have given as 100 centimeter square. So you have to consider this square area on a surface whose equation is given by what? Is given by x plus y equal to 1. So they have given the equation of a surface, right? So the equation of the surface is x plus y is equal to 1. So all the points on that plane, okay, all the points on that plane which are going to all the points on that plane has to satisfy this equation. Yes or no? That is x plus y is equal to 1, right? So whatever the points that are going to satisfy this equation, so all those points are going to lie on that plane here, right? Okay, so you can have infinite number of solutions for this one, and hence you can have infinite number of points on that surface, which means that surface represents some infinite surface, right? Okay, so it represents infinite surface, and here we are having the condition for the values of x and y only, right? Okay, we don't have any condition on z. So that means on this plane z can vary from where to where? It can vary from minus infinity to plus infinity, right? So z values can vary from minus infinity to plus infinity, but you are going to have the conditions on x and y values. So you have to choose the x and y values such that it has to satisfy this equation. Only those points are going to present on that plane, right? Okay, okay. So that means here, if you observe here, so let us say this is a x axis and this is y axis. So you are having the equation as x plus y is equal to 1. Okay, let us assume x equal to 0 here, x equal to 0. At x equal to 0, y value is equivalent to what? Is equivalent to 1. Y value is equivalent to 1, right? Okay, and when y equal to 0, x value is equivalent to what? X value is equivalent to 1. So when y equal to 0, x value is equivalent to 1, right? Okay, okay. So here so here you are going to get what? So from here I can get y is equal to what? Y is equal to minus x plus 1. So I can form a line here. I can form a line from this equation. It is just like y equal to mx plus c. So I can form a straight line like this, right? Okay. Now here there is no condition for z here. So z can vary from where to where? Z can vary from minus infinity to what? Minus infinity to plus infinity. So now you can extend this line. You can extend this line from minus infinity to what? From minus infinity to plus infinity. So if you go on place this line along z here, so z is coming out of the board. Yes or no? Z axis is coming out of the board. So if you place such type of lines continuously up to what? You can place such type of lines continuously up to what? Z equal to plus infinity, and also you can place such type of lines continuously up to what? Z equal to minus infinity. So this is going to form what? This is going to form an infinite surface. Yes or no? So that surface they have given, right? Okay, and the wave is propagating. The wave is propagating in which direction? The wave is propagating in positive x direction. So that means the wave is propagating in positive x direction. That means the wave is propagating like this. So that means the time average Poynting vector is going to point along the direction of what? Along the direction of wave propagation. Okay, so here it is going to form an infinite surface like this, right? Okay. Okay, so it is going to form some infinite surface like this. So it will extend up to z equal to plus infinity, and it will go up to z equal to minus infinity. So this is the surface here. So the surface is like this, right? And the wave is propagating like this, right? Okay, okay. Yeah. So they are saying that consider a square area of 100 centimeter square. So on this plane, just consider a square area of 100 centimeter square. 100 centimeter square. Okay, so on this plane you have to consider 100 centimeter square area. You have to determine the power flow through this surface here. You have to determine the power flow through this surface. Okay, Okay, how you can determine the power flow through this surface here? So this is nothing but what? This is nothing but A bar. So let us say this surface area, this square area I am representing as A bar here. This square area I am representing as A bar, right? Okay, so the power penetrating through this small differential area, let us say this is small differential area dA bar. So the power penetrating through this small differential area is nothing but what? S average dot what? Dot dA bar. If you want the power flow through this surface area, what you have to do? You have to integrate throughout this surface, right? So this is the expression to determine what? To determine the total power average, total average power through that given surface, right? Okay, so first you try to determine S average here. So S average is equivalent to what here? Is equivalent to, so it is free space, means it is lossless medium, that is equivalent to half into what? Half into E square by eta naught, and the wave is propagating in x direction, so that is a AX cap. So what is the amplitude of electric field here? The peak amplitude of electric field they have given as what? 24 pi. 24 pi. This is the peak amplitude of the electric field. So here substitute that. So what you are going to get? Half into 24 pi whole square divided by what? Eta naught is 120 pi AX cap. So watt per meter square. Okay, so you can easily calculate this one, that is 1 by 2 into 24 pi into 24 pi divided by 120 pi AX cap. So here pi will get cancelled. So 2 12 2s are here, 12 10s are, so and here 2 will get cancelled. So you are going to get what? 24 by 10, that is 2.4 AX cap watt per meter square. So this is time average Poynting vector here. So if you observe here, this time average Poynting vector is independent of what? Is independent of space. You are getting some constant value. Yes or no? Spatially it is not varying. Yes or no? S bar average we got it as what? 2.4 AX cap watt per meter square, right? This is what you are going to get. And here they have given the magnitude of area here. See, A bar is going to have what? A bar is going to have magnitude as well as what? As well as direction. Magnitude as well as what? Direction, right? So we know the magnitude. Magnitude is nothing but 100 centimeter square. Now how to write the direction of that surface? We know that the direction of the surface is always given by the normal drawn to that surface. Yes or no? The direction of any surface is given by what? Is given by the unit normal drawn to that surface. So the direction is represented by what? Is represented by the unit normal drawn to that surface. Okay, but here if suppose they have given x equal to constant plane as the surface here, then the direction will be what? The direction will be AX cap. Okay, if they would have given y equal to constant plane, then the direction of the surface will be AY cap. If they would have given z equal to constant plane, then the direction of the surface you can consider as AZ cap. But here they have not given these surfaces. So what they have given? They have given the surface equation as x plus y is equal to some constant, that is x plus y is equal to 1. So it is just like the generally the equation of any plane here, the equation of any plane is given by, in generally if the equation of a plane is given as ax plus by plus cz is equivalent to d. If suppose they have given the equation of a plane in this manner. Okay, so this represents a equation of what? Equation of a equivalued plane, or equation of a okay, equation of a you can say that means for all x, y, z values on that plane, okay, it has to satisfy that equation. Okay, all those points are going to lie on this plane. So whatever the points that are going to lie on this plane, they have to satisfy this condition here, right? Okay. So we can call this as a equation of a equivalued plane, or equation of a constant surface. You can call it as equation of a constant surface. Why I am calling it as constant surface here? Because all the points if you substitute all the points on the plane, on that surface, it is going to give you this constant value d, right? Okay, so that's why we call it as what? Equation of a constant surface or equivalued surface, right? Okay, okay. So in general, this is the representation here. So if you draw the normal to this plane, to this arbitrary plane, okay, then the normal, if you draw the normal, okay, then you are going to get the normal vector to this plane as ax cap plus bay cap plus caz cap. Just write down the coefficients of x, y and z. Just write down the coefficients of x, y and z. You are going to get what? You are going to get normal vector to the plane, normal vector to the plane. Okay, but if you want the direction of that plane, we have to represent the direction with the help of what? Unit normal. So what is unit normal here? A unit normal in general we will represent with an cap, which is equivalent to what? Which is equivalent to normal vector divided by its magnitude. So that is nothing but ax cap plus what? Plus bay cap plus caz cap. So take this vector and divided by its magnitude, you are going to get what? You are going to get the unit normal. Okay. Okay. So what is the difference between normal vector and unit normal vector here? So for this one, the magnitude is square root of a square plus b square plus z square, whereas for this one, the magnitude will be equivalent to what? 1, right? That is the only difference. Okay. So unit normal will always represents what here? It represents the direction of what? Direction of surface, right? So in the given problem, what is the equation of the plane they have given? They have given the equation of the plane as x plus y is equal to 1. So if you compare this with this arbitrary equation, so what is a value? So from here, a value is equivalent to 1. The coefficient of y, that is b value, is also equivalent to 1, and c value, that is coefficient of z, c value must be equal to 0, and d value must be equal to 1. Right. So for this one, what is the unit normal vector? So that is nothing but ax cap, that is 1 into ax cap, plus bay cap, that is 1 into ay cap. C is 0. So divided by square root of what? A square plus b square plus c square, that is 1 square plus 1 square. So which is equivalent to what? Which is equivalent to ax cap plus ay cap divided by what? Divided by root 2. So this is the unit normal vector, right? So now what is a bar here? A bar is equivalent to magnitude of a bar into what? An cap. So what is magnitude of a bar? That is nothing but 100 centimeter square. So if you convert that into meter square, I can write it as what? 100 into 10 power minus 4 meter square, right? That is the magnitude of area. And An cap is nothing but what? Is nothing but ax cap plus what? Ay cap divided by what? Root 2. So you have determined the area, and you have determined what? You have determined S average here. You have determined S average here. Okay. So if you substitute this S average, right? Okay. If you substitute this S average in the formula, so that is the total average power is equivalent to what? Double integral S average. What we got? We got what is the value we got here? 2.4. Okay. 2.4 ax cap. So S average is nothing but 2.4 ax cap. So this is S average. This is S average. Okay. Dot dA bar. Dot dA bar. Now if you observe here, dA bar. Here dA bar. What are the variables here? What are the variables on this surface? X and Y are variables. Yes or no? Okay. So here if you observe this S average is independent of what? Is independent of integration variables. Yes or no here? Okay. So anyway, you are going to have here integration variables. Yes or no? Integration variables means here you are going to have some spatial variables. Okay, dx, dy like that. Right. So, but here S average is independent of what? Independent of those integration variables. It is independent of what? Spatial function. Yes or no? It is independent of space here. So that's why you are going to get S average independent of what? Integration variables. So if it is independent of integration variables, you can take it out of the integration. So that is, you can write it as what? You can write it as simply 2.4 AX cap. You can take it out of the integration. So this is nothing but S average. S average. Okay, so double integral dA bar represents what? Represents the total surface area. So that is nothing but A bar. That is nothing but A bar, right? Okay, so this is the total average power flow through that given surface. So this A bar is going to have what? This A bar is going to have both magnitude, right? It is going to have both magnitude as well as what? Direction, right? And this is nothing but what? This is nothing but A bar. This is nothing but A bar, right? Since S average is independent of what? Integration variables, the total time average power flow through the given surface, I can represent it as what? Simply S average dot what? Dot A, right? In this manner I can represent. Now here we know this A bar value is how much here? 100 into 10 to the power of minus 4 meter square, and this direction is nothing but AX cap plus AY cap divided by root 2. Just substitute all this here. Just substitute all this. Okay, so here if you do the dot product, between this vector and this vector, what you are going to get? Only AX cap components will get multiplied. AY cap component, AX cap dot AY cap component will become what? Will become 0. Okay, so just multiply the X component terms, then what you are going to get? 2.4 into what? Into 100 into 10 to the power of minus 4 divided by what? Divided by root 2. Right, this is the value you are going to get, right? You can calculate this one here. So this is the total average power flow through the given surface, right? So in this manner we can determine. Vishwas, sir, please don't private this session. My health is not good. Okay. So it will be present here up till GATE exam. This video will be available, I think so. Right? Okay. So don't worry about that. Right. So this is the time average power flow here. So this is how you have to determine the time average power flow through a given surface. Okay. See, instead of these calculations, you have to understand the method and procedure and also the analysis, how we are doing the analysis. Okay, if you understand this analysis, then whatever may be the problem here, whatever may be the problem under this model, you can easily solve, right? Okay. So if you have understood analysis clearly, then it is equivalent to doing 10 to 20 problems, right? Okay. The same model, you can solve any problem based on this model here. Okay. So we have done it for a lossless medium, right? They may ask you for a lossy medium also. Okay, you know for lossy medium how to determine S average, right? Okay, and you know how to determine whether it is lossy medium or lossless medium. This surface integration is going to be same, right? Okay. So I hope this thing is crystal clear, right? Okay. So with this we have completed this Poynting theorem topic. So we have covered how to determine this time average Poynting vector and also how to determine the power flow through a given surface. Okay, right? Okay. So next I am going to start transmission lines here. So here I am taking break here. Take break for 5 minutes. So break for 5 minutes. So after 5 minutes break we will start here. We will start after 5 minutes break. So now it's 12:05. So we'll meet at 12:10 p.m. Okay. Okay, so break will be 5 minutes. So after 5 minutes we'll meet at so now it is approximately 12:05, so we'll meet at 12:10, right? Okay. 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 So welcome back. Okay. So we will start transmission lines here. So next topic we'll start transmission lines. Right. Okay. So I will briefly go through the most important topics of this transmission lines. Okay. Okay. See here, the first one is the most important topic here in transmission lines is transit time effects. So first of all, you have to know what do you mean by transit time effects. So which is represented by TR, and the second one is distributive nature on the transmission line. So distributive nature on the transmission line. Okay. Okay. So see here. See, if you consider a transmission line here, if you consider a transmission line, so at one end you are going to connect some source, right, and at the other end you are going to connect some load, right. So this is the load section and this is the source section. Okay, and this is nothing but transmission line. So let us say the length of the transmission line is L. Okay, so the time taken for the signal to travel from source to load here, the time taken for the signal to propagate from source to load is called as what? Is called as transit time. So let us assume the wave along the transmission line is propagating with a velocity v, Vp. So that is phase velocity. Okay. So then I can represent I can represent the transit time as what here? Transit time as the length is nothing but what? L, and the velocity is nothing but V. So L by V, L by phase velocity. So the units of L is meter, the units of phase velocity is meter per second, meter will get cancelled, the units of TR is nothing but what? Seconds. So the time taken for the signal to travel from where to where? To travel from source to load is defined as what here? Is defined as transit time. So how you can determine that transit time here? So the transit time is nothing but L by what? L by velocity. Okay, the length of the transmission line is L, and the velocity with which the signal is propagating from source to load is nothing but Vp. So L by Vp is going to give you what? The time taken for the signal to travel from source to load. So this time taken by the signal to travel from source to load, we call it as what? We call it as a transit time. Transit time. Okay. Okay. So now let us assume this location as x is equal to 0. Let us assume this location as x is equal to 0. So I am considering this as x direction here, right. So this location x equal to 0, then the length of the transmission line is L. So this location will be what? X equal to L. Okay, let us assume you have applied a signal here V naught into what? Cos omega t. Cos omega t. Okay, cos omega t. Right. So this is the signal you have applied here. So after some time what will happen? This signal is going to shift from this location to what? This location to load location. So once it reaches to the load, I can represent the signal as what here? At x equal to L, I can represent it as V naught into what? Cos of omega t minus what? Minus beta L. So where beta L is the change in phase shift over the length L here. Change in the spatial phase shift over the length L. Okay, so as the wave propagates from source to load, it is going to shift from one location to another location. So that shifting of the wave we can represent in terms of what? Traveling wave. So the traveling wave along this L direction we can represent as what? V naught into what? V naught into. See, here we have assumed this in x direction. So I can represent it as cos of omega t minus beta x. Okay, so here at this location, at the source, x is equal to 0, so we are getting v naught into cos omega t, and at x equal to L, we are at the load. So at the load, the signal becomes what? V naught into cos of omega t minus beta L, right? Okay, okay. So now see here. So that means here the spatial phase shift here, the spatial phase shift from source to load is how much? At the source, the spatial phase shift is 0, because at location x equal to 0, beta x value will become 0. Understood? And at x equal to L, the phase shift is beta L. So from x equal to 0 to x equal to L, what is the change in phase shift with respect to L is nothing but beta L, right? So beta L is the change in phase shift over length L. Okay, so change in spatial phase shift. Yes or no? Or you can simply write change in phase shift over length L, Okay, over length L means you have to understand that it is spatial phase shift, right? Okay, so now when we can neglect this spatial phase shift, and when we cannot neglect this spatial phase shift, it all depends upon this transit time here. This all depends upon this transit time, right? Okay, so here the applied signal is going to have some time period. So the time period of the signal I am representing with t, right? And here this tr represents transit time. So we are going to compare this time period of the signal with respect to what? With respect to this transit time of the signal, right? And also the length of the signal is nothing but L, and the wavelength of the signal is nothing but what? Lambda signal. Okay, so we are going to compare the length of the transmission line with respect to what? With respect to wavelength of the signal. So based on this comparison of L to lambda and TR to T, we can decide when we have to include the transit time effects and when we have to neglect the transit time effects. So what happens if we include the transit time effects, and what happens when we neglect the transit time effects? So those things we are going to see. Okay, I will explain in a very brief manner here, brief and simple manner, right? So here beta L, when we can neglect beta L. So that means whenever beta L is very small, so that means if beta L tends to 0, okay, if beta L tends to 0, then we can neglect the spatial phase shift from source to load. Yes or no? So that means if I make this length as delta x, where this delta x tends to 0 here, if this delta x tends to 0, so that means the source and load both are almost present at the same location. In that case, this length will be very much negligible. In that case, beta L can be neglected. Yes or no? Okay, so in that case we can neglect what? We can neglect the spatial phase shift. This is one case, right? So what are the other cases here? What are the other cases when we can neglect this beta L, that is spatial phase shift? Tell me. When we can neglect the spatial phase shift, tell me. So if beta L is negligible, we can neglect the spatial phase shift. So when we can neglect this beta L, okay, so actually this beta L is equivalent to what? Is equivalent to, beta is nothing but 2 pi by lambda into L, which is equivalent to, I can write it as 2 pi into L by what? L by lambda. So here lambda represents the wavelength of the signal, L represents the length of the transmission line, right? So now from here I can say if lambda of the signal, if the wavelength of the signal is far greater than the length of the transmission line, then what will happen? We can neglect L by lambda ratio. Yes or no? If wavelength of the signal is very much greater than the length of the transmission line, then we can neglect what? Then we can neglect L by lambda ratio. So if you neglect this L by lambda ratio, okay, so if this L by lambda is negligible, then this beta L is also going to be what? Is also going to be negligible, is also going to be negligible. Okay, so we can neglect, okay, if we can neglect whenever L by lambda ratio, we can neglect L by lambda ratio if lambda of the signal is far greater than what? Far greater than length of the transmission line. This is one case. So I can write the same expression here. I can write the same expression like this. So that is 2 pi into, so what I am doing here is I am multiplying with frequency and dividing with frequency. So L into F divided by what? Divided by lambda of the signal into what? Into frequency, right? Okay. Okay, so lambda into F I can represent as what? I can represent the velocity of the signal, right? So L by V, lambda into F is nothing but V. So L by V represents what? Transit time. So I can represent this as 2 pi into what? 2 pi into TR. So L by V I am representing with TR. So this frequency, this is the frequency of the signal. So what is the relation between the time period and frequency here? So frequency I can represent it as what? 1 by time period of the signal, 1 by time period of the signal. So if I replace F with 1 by time period of the signal, I am going to get what? TR by time period of the signal, right? Okay, so this is nothing but what? This is nothing but beta L only. I have represented beta L in terms of what? Here L by lambda. Here by multiplying with frequency and dividing with frequency, I have represented the same beta L in terms of what? Transit time and time period of the signal. So when we can neglect this beta L here, when we can neglect this beta L, so if time period of the signal or if transit time is far less than what? Far less than time period of the signal. So in this case we can neglect what? We can neglect TR by T ratio, TR by T ratio. Okay, so if we neglect TR by T ratio, in that case we can neglect what? We can neglect this beta L, right? Okay, okay, yeah. So right, okay, okay. So we can neglect beta L, we can neglect beta L whenever the transit time is far less than what? Far less than the time period of the signal, or we can say if TR by T ratio is negligible, then in that case we can neglect beta L, or we can say the same thing in another manner, that is if the length of the transmission line is far lesser when compared to lambda of the signal, or I can say if lambda of the signal is far greater than length of the transmission line, in that case also we can neglect beta L. So if we neglect beta L here, if we neglect beta L, so if we neglect beta L, that means beta L is tending to 0, right? Okay, so that value is tending to 0, so you can neglect this beta L. So if you neglect this beta L, this V0, if you neglect this beta L, right, so then this x value is lesser than what? Lesser than L only. Okay, so you can neglect this beta x also, right? So throughout this length you can neglect this spatial phase shift here, you can neglect this spatial phase shift. So under that condition, what will happen? You can consider only what? Along the transmission line, okay, along the transmission line you can consider simply the signal as what? V0 of cos omega t. So you can neglect the spatial variations along what? Along x, right? Okay, so when it is going to happen? Whenever TR by T ratio is neglected or L by lambda ratio is negligible. That means if the wavelength of the signal is very large, the wavelength of the signal is very large when compared to L, means generally it happens at what? At low frequencies or not? Yes or no? Generally it happens at low frequencies. So for low frequency signals the wavelength is going to be very high. So if the wavelength is very high such that such that it is far greater than what? Far greater than length of the transmission line, then in that case we can neglect what? We can neglect this change in phase shift with respect to what? With respect to length. Understood? Okay. So if you neglect beta L, then the voltage will become a function of what? Only time. Right. So at any instant of time here, at any instant of time, whatever the voltage that you are going to see at the source, the same voltage you are going to see throughout the circuit, throughout the transmission line, and at the load also. Right. So here the voltages and current, similarly you can analyze with respect to current also. Instead of taking voltage signal, if you take the current signal, you are going to get the same analysis. Okay. So here you can consider the voltages and signals as what here? We can consider the voltages and signals as functions of what? As functions of time. Yes or no? We can neglect the spatial variations of voltages and currents along the transmission line in this case. So that happens at what here? At low frequencies. So low frequencies means what here? At those frequencies, L by lambda ratio is negligible, and also what? And also TR by T ratio is also negligible. So at low frequencies, so what is the conclusion we can make? So at low frequencies, such that L by lambda ratio is negligible, or I can say TR by T ratio, okay. So such that L by lambda ratio or TR by T ratio is negligible, then such type of frequencies we are considering as what? Low frequencies. So at this low frequencies, we can neglect what? We can neglect spatial variations. We can neglect the spatial variations. So which means we can neglect what? We can neglect beta L. We can neglect beta L. So in this case, the voltages and currents. So in this case, V and I will become what? Will become only functions of what? Only functions of time. So they are independent of what? They are independent of space. Right. So that's why in your circuit theory also we are going to deal with what? We are going to deal with only low frequency signals here. Right. So why means at low frequency signals only, low frequency signals means you have to keep this point in mind. Low frequency means such that L by lambda ratio is becoming negligible, at the same time TR by T ratio is also becoming negligible. So those type of frequencies we call them as low frequencies. So at those frequencies, voltages and currents will become only functions of time. So whenever they become only functions of time, then only KVL and KCL are valid. So if you observe in circuit theory, okay, always you are going to consider only the time variations of voltages and currents. You don't consider the length of the circuit in case of network theory or circuit theory. Yes or no? Okay. Why means there we are dealing with low frequency signals. At low frequency signals, there is no need for you to worry about the spatial variations along the length of the circuit, because that spatial variations we can neglect here, because at those low frequencies these ratios are negligible, and hence it will become independent of what? Independent of circuit length. Okay. So it will become simply functions of only time. So if it becomes simply functions of time, then KVL and KCL are valid at low frequency signals. Okay. But if you consider high frequency signals here, so what do you mean by high frequency signals? So high frequency signals, okay. So if you consider high frequency signals, so then in that case lambda value will be what? Lambda value will be very less. So if lambda value is very less, L by lambda ratio will become what? Significant. If L by lambda ratio will become significant, then beta L will also become significant. If beta L is becoming significant means the change in phase shift along the length of the transmission line is becoming significant. Understood? That means spatial variations along the length of the transmission line is also becoming what? Is also becoming significant. So in this case you cannot neglect what? Spatial variations. Right. So at high frequency signals means L by lambda ratio becomes what? Becomes significant. right? So L by lambda ratio can also be written as what? TR by T ratio. So either the ratio of L by lambda or TR by T ratio will become what? Will become significant. So then those frequencies we call them as what are high frequency signals. So at this high frequency, beta L is the change in phase shift between source and load. Okay, so this change in phase shift between source and load will become what? Will become significant. Yes or no? Will become significant. Why here? Beta L is equivalent to what? Beta L is equal to, you can write it as what? 2 pi into L by lambda, or what? 2 pi into what? 2 pi into TR by T. So whenever this L by lambda or TR by T ratio becomes significant, this beta L will also become significant. So the change in phase shift along the length of the transmission line, whenever it becomes significant, you should not neglect this spatial phase shift here. So that means now the voltages and currents will become functions of what? Both time as well as what? Phase. Because now here you should not neglect the spatial phase shift, right? Okay, so in this case voltages and currents will become functions of what? Both space as well as what? Both space as well as time. Both space as well as time, right? Okay. So once they become functions of both space as well as time, okay, we know that we cannot apply KVL and KCL. So once the voltages and currents will become spatial functions here, if they are functions of time, then only we can apply KVL and KCL. We can apply KVL and KCL happily. Okay, once they become functions of length also, okay, then you cannot apply. It is not possible. And we cannot apply this KVL and KCL. So KVL and KCL are ruled out whenever this voltages and currents becomes functions of what? Functions of length. Okay, so here KVL and KCL are what? Are ruled out. Okay, so we cannot apply this KVL and KCL. You cannot apply KVL and KCL. Okay, KVL you cannot apply, KCL also you cannot apply. So these are ruled out here. So this happens at high frequencies. So whenever at high frequencies, this transit time will become comparable to what? Comparable to time period of the signal, and also the length of the transmission line becomes comparable to what? Lambda of the signal. So in this case, these ratios will become significant, and hence beta L will also become significant. Beta L represents the change in phase shift over the length L. Okay, that length L is nothing but what? The distance between source and load, right? Okay, so once it becomes significant, then voltages and currents becomes functions of what? Both length as well as what? Time. So once they become functions of length and time, so then in that case, since they are becoming functions of length, you should not apply KCL and KVL in this case, right? Okay. So here throughout our transmission lines, we will assume that this condition is valid. So that means we are going to deal with the high frequency signals such that it is going to satisfy this condition. So once it satisfies this condition, throughout our transmission lines, we are going to consider our voltages and currents on the transmission lines as a functions of what? As a functions of length and time. Okay, so here we should not neglect this transit time. Right, we have to include this transit time because it becomes comparable to time period of the signal, right? So that's why this ratio is becoming significant. So here transit time effects you should not neglect. So once you if you don't neglect the transit time effects, then under that condition the voltages and currents will become functions of what? Length as well as time. Okay. So now if you neglect the transit time effects, that means TR is negligible when compared to time period of the signal. Okay, so in that case you can neglect this ratio. If this ratio is neglected, then this beta L can also be neglected. That is spatial variations you can neglect. So in that case voltages and currents becomes only functions of time. So under that condition you can happily apply KVL and KCL. So that is valid for circuit theory. But whereas in our transmission lines, voltages and currents will consider as what? Functions of both space as well as what? Time, because here we are going to include the transit time effects here, right? Okay, because in transmission lines we are going to deal with the high frequency signals such that L by lambda ratio and TR by T ratio cannot be neglected, right? Okay, okay. So I hope these points are crystal clear here, right? Okay, okay. Right. Next, on the transmission line. So on the transmission line, the resistance value, inductance value, and capacitance and conductance, all these parameters are distributed or having distributive nature along the transmission line. So we can develop the circuit model for this transmission line here. Okay, so what is the circuit model of this transmission line? So generally we'll represent here the resistance. Okay, so here the resistance, and here inductance, and here capacitance, and here conductance. So capacitance, inductance, resistance. Okay, you can model the transmission line. I am not going into the details how we can model these things and all that, right? Okay, so here this is the length of the transmission line. So generally we will consider this delta x tends to 0. Okay, so delta x tends to 0. So by considering the length of the transmission line, tends to 0. So that means whenever it tends to 0, right, we can apply what? Whenever the length of the transmission line tends to 0, right? So then we can apply what? We can apply KCL and KVL under that condition. I have told that here. Okay, whenever delta x tends to 0, so source and load we are assuming at the same location, almost at the same location, then in that case you can neglect the spatial variations. In that case you can happily apply what? KVL and KCL. So with the help of KVL and KCL here, to this circuit, when we can apply KVL and KCL to this circuit, by assuming the length of the circuit or the length of this transmission line tends to what? Tends to 0. So under this assumption we are going to apply KVL and KCL to this circuit here. So here let us say at this location, this is x is equal, this location I am considering as x. So this location I am considering as x plus what? X plus delta x. Right, this location will become x plus delta x if I consider this location as x. So here the voltage that I am applying here as is V of x. So the voltage here is nothing but V of x plus delta x, right? And here the current that is flowing is I of x, and here the current that is leaving from this node is nothing but I of x plus delta x, right? Okay, so by applying KVL and KCL, right, we are going to get the equations of voltages and currents. Why we are applying KVL and KCL? We are assuming that this length is tending to 0. So with that assumption you can happily apply KVL and KCL, right? Okay, okay. So by applying KVL and KCL you are going to get the equations of voltages and currents on the transmission line in this manner. So that is dou square V of x by dou x square is equivalent to gamma square into what? Into V of x. So similarly you are going to get dou square I of x by dou x square is equal to what? Gamma square into I of x. So these are the equations that we are going to get. So I am not solving this differential equation here, so I am directly writing the solution for this one. So the solution for this one will be V of x is equivalent to V plus into e power minus gamma x plus V minus into e power gamma x. So here the solution for I of x will be in the same manner, that is I plus into e power minus gamma x plus I minus into e power gamma x. So these are the solutions in terms of what? In terms of space, of voltages and currents. Okay, so here also we are going to deal with the time harmonic voltages and currents. So that means here also the voltages and currents are going to vary with respect to what? Are going to vary sinusoidally with respect to time. So always, whether it is electric field or magnetic field, or here it is voltages and currents, so both are nothing but what? Time harmonic in nature. Throughout our subject we are going to deal with time harmonic signals only, right? Time harmonic means those fields or the signals are going to vary with respect to what? With respect to time sinusoidally. Okay, okay. So the complete solution for voltages and currents will become what? V of x comma t, which is equivalent to V of x into e power j omega t, where V of x is equivalent to what? V plus e power minus gamma x plus what? V minus into e power gamma x multiplied by what? Multiplied by e power j omega t. So similarly, I of x comma t is equivalent to what? Is equivalent to I of x into what? E power j omega t, which is equivalent to what? Which is equivalent to I plus into e power minus gamma x plus I minus into e power gamma x multiplied by what? Multiplied by e power j omega t. Right? Okay? Okay. So these are the solutions for voltages and currents that we are going to get. Right? So here where gamma is equal to, where gamma is equivalent to what? Is equivalent to alpha plus j beta. So the definitions of gamma, alpha and beta already I have given here. So the same definitions equivalently valid here also. Gamma represents propagation constant, alpha represents attenuation constant, beta represents phase constant. Right? Okay. So the expression for gamma here you are going to get as square root of r plus j omega L into what? Into z plus j omega c. So this is the expression for gamma here, gamma. Okay. So since it is a complex quantity, okay, it is going to have a real part as well as what? As well as imaginary part. Right? Okay. So since it is having real part, that is alpha is not equal to 0 here. So if alpha is not equal to 0, the line is going to behave as what? The line is going to behave as lossy line. Okay. So this is the propagation constant for which line here? For a lossy transmission line. Okay, lossy transmission line means here alpha is not equal to what? Alpha is not equal to 0. Right? Okay. Okay. So now see here, but from here onwards what we are going to do here is see, up till now we have considered the voltages and functions as what? As a functions of x here, right? See, from here onwards we will mainly focus on this spatial variations here. Okay, so we know that with respect to time they are going to vary sinusoidally, that we know. Okay, so whether we represent e power j omega t or not in the solutions, you have to always keep in mind that you always keep in mind that always here you must have what? E power j omega t term. Whether you represent it or not, inherently e power j omega t term is going to be present for what? For v and I. That's what you have to always keep in mind. Okay, so there is no need to represent e power j omega t every time here, because we know that e power j omega t must be present. Okay, okay, okay. So now here we have assumed that this is the source, right? And here this is the load. Here we have considered the load, right? Okay, so we have considered this direction as x. Right? So this is x is equal to 0. We have considered this as x equal to L. So now what I am going to do here is, I am going to consider the reference. Now here I am going to consider the reference as load here. Okay, so here I am going to consider this as L is equal to 0. Right? So this is the reference location I am considering now. So previously, whenever I am considering x as the variable, I have considered the reference location as source. Right, and I have started moving from source to load. So as I move from source to load, I have considered the variable as x. Now I started moving from where to where? From load to source. So now I am considering the load as what? Load as my reference point. So now I am moving from load to what? Load to source. So as I move from load to source, what is going to vary? the length of the transmission line is going to vary. So as I move from load to source, this L is going to increase. Okay, so if you observe, as I move from load to source, L is increasing, whereas if I move from source to load, X value is increasing. So both are what? Both are in opposite directions. So I can replace wherever you are having X, there I can replace with what? I can replace with minus L. So if I replace with minus L, then I will get the expressions for voltages and currents in terms of what? In terms of length. Okay, and you have to keep in mind that this length, we are moving from where to where? We are moving from load to source. Right. So I am going to write the expressions for voltage and current in terms of what? In terms of L and T. So this is equivalent to V plus previously we are having e power minus gamma x. Okay, wherever you are having x, they are replaced with minus L. Wherever you are having x, they are replaced with minus L. They are replaced with minus L. They are replaced with minus L. Okay. So what you are going to get? Tell me. So you are going to get V plus into e power gamma L plus what? V minus into e power minus gamma L into what? Into e power j omega t. So I have already told that there is no need to represent every time e power j omega t, because automatically whether you represent or not, you have to understand that inherently that e power j omega t term must be present. Okay, because here we are dealing with time varying signals, right? Okay. Okay. Next, similarly, I of L comma T is equivalent to what? Is equivalent to I plus e power gamma L plus what? I minus into what? E power minus gamma L into what? Into e power j omega t. Right. So these are the equations or the solutions of voltages and currents on the transmission line. Yeah, these are the complete solutions of voltages and currents on the transmission line. So now if you observe here, we have already studied that this represents a forward traveling wave. This multiplied by this one represents forward traveling wave, and this multiplied by this one represents what? Reflected wave. Okay, so the combination of these two represents what? The combination of these two represents a standing wave pattern. Standing wave pattern. Okay, so here also this represents what? This represents, this term represents forward traveling wave. This term multiplied by this one represents reflected wave. So the total, the summation of forward traveling wave and reflected wave is going to form what? Standing wave pattern. Right. So that means we are going to see the voltages and currents as a standing wave patterns on the transmission line. Right. Okay. Okay. Yeah. So now see here. Now see here. So on the transmission line, you are going to have voltages and currents as what? Standing wave patterns. So why we are going to have standing wave patterns here? So if you consider the transmission line here, so let us say this is the load impedance ZL. Right, and here you are having some source, right? Okay, so generally this transmission line is going to have some characteristic impedance Z0 here, some characteristic impedance Z0. Okay, so if suppose whenever the voltage wave or current wave is traveling along the transmission line, okay, so this forward traveling wave, so initially whenever you apply the signal, the voltage signal is going to travel from source to load. Yes or no? This is nothing but what? Forward traveling wave. So whenever this forward traveling wave is moving on the transmission line, it is going to see the characteristic impedance of the transmission line, that is Z0. So here we are going to define the characteristic impedance of the transmission line as what? Forward traveling wave voltage. Forward traveling wave voltage to what? To forward traveling wave current. Forward traveling wave current. So if you take the ratio of forward traveling wave voltage to forward traveling wave current, you are going to get the expression for characteristic impedance. So if you do that, you are going to get square root of what? The expression for this one, you are going to get square root of R plus j omega L by Z plus j omega C. By Z plus j omega C. So this is the expression you are going to get for the characteristic impedance. So if you observe here, if the operating frequency is fixed, then omega is fixed here. Yes or no? So for a given operating frequency omega is fixed. So if omega is fixed, then this Z0 is particularly depending upon what? Is particularly depending upon R, L, Z and C. So R, L, Z and C are going to depend upon what? Are going to depend upon a transmission line. So how you are designing the transmission line? Okay, that means with which material you are designing the transmission line. So based on that, this R, L, G and C values are going to depend. Okay, so what is the material that you are using in order to construct the transmission line? What is the distance that you are maintaining between these two conducting lines? Okay, so on all those parameters, this R, L, G and C are going to be dependent. Okay, so once the transmission line is designed with a particular type of material, okay, by maintaining some distance between the two conductors, okay, then this R, L, Z and C are going to be fixed for that given transmission line, right? So that means once you design a transmission line, the characteristic impedance of the transmission line will be fixed. So how you can calculate the characteristic impedance here? That is the ratio of forward traveling wave voltage to forward traveling wave current. Okay, or you can write Z0 as what? Z0, forward traveling wave voltage to forward traveling wave current. Okay, right? Okay, okay. So similarly, so this is a forward traveling wave voltage means V plus what? V plus e power gamma L into e power j omega t, and this is nothing but what? This is nothing but V minus into e power minus gamma L into e power j omega t. So this term will get cancelled. Okay, so by taking this ratio you can determine what? Forward traveling wave voltage to forward traveling wave current, forward traveling wave current, so you have to write here I plus into what? E power gamma L. So this term will get cancelled, right? Okay, so e power gamma L will also get cancelled. So you are going to get V plus by I plus, right? So which means here it is independent of what? It is independent of length of the transmission line. So characteristic impedance is independent of what? Independent of length of what? Length of transmission line. Okay, why here L term will get cancelled. So this e power j omega t will also get cancelled. So Z0 is independent of what? Is independent of length of the transmission line. So at each and every location on the transmission line, okay, you are going to see the same value of the characteristic impedance, and this characteristic impedance is fixed. It is fixed for a given transmission line, So once you design the transmission line with a particular material, okay, once the design is completed, then the characteristic impedance of the transmission line is fixed here, right? And it is independent of what? Length of the transmission line. So wherever, at whatever the location you will move on the transmission line, the characteristic impedance that you are going to see is going to be same. And what do you mean by this characteristic impedance? It is the ratio of forward traveling wave voltage to forward traveling wave current. Right? Okay? Okay. Right. Right. And here in the derivations we will get V plus by I plus is equivalent to Z0, and also you are going to get, similarly if you consider only reflected wave here, I am not considering forward wave. If you consider only reflected wave will also represent what? Traveling wave. Okay, traveling wave voltage to traveling wave current is going to give you the characteristic impedance. Right. So here if I take only reflected wave, if I consider only reflected wave, then if you take the ratio of reflected wave voltage to reflected wave current, you are going to get what? Minus of what? You are going to get minus of Z0. So that means Z0 you can write it as what? Minus of V minus by what? Minus of V minus by I minus. So minus of backward traveling wave voltage or reflected wave voltage to reflected wave current. So one thing you have to keep in mind is characteristic impedance is defined with respect to traveling wave, traveling wave voltage to traveling wave current. So if it is forward traveling wave, you have to consider the forward traveling wave voltage to forward traveling wave current. So if it is the reflected wave or backward traveling wave, then you have to consider the characteristic impedance as minus of what? Minus of reflected traveling wave voltage to reflected current wave voltage, reflected traveling wave current, right? Okay. So finally Z0, if you do these things, you are going to get finally the expression for Z0 as a square root of what? Square root of R plus j omega L by Z plus j omega C. That is the expression for characteristic impedance, right? Okay. So the one thing you have to remember is characteristic impedance of a given transmission line is fixed, right? It is independent of the length of the transmission line. It depends only upon the design of the transmission line, right? Okay. And this characteristic impedance is defined with respect to traveling wave patterns, right? That's what you have to keep in mind, right? Okay. Now on the transmission line, so whenever the wave is propagating like this, right? So if you consider the forward traveling wave, it is going to see the characteristic impedance of Z0. So once it reaches to the load here, let us assume at load the load impedance is ZL. So let us say this ZL is not equivalent to Z0. This ZL is not equivalent to Z0. So whenever it travels to the load, at load it is seeing some other impedance which is other than what? Characteristic impedance. So it is seeing some different impedance when compared to characteristic impedance. Okay, so that means at load you are having what? You are having a impedance mismatch. So because of this impedance mismatch, what will happen? A part of this wave will get transmitted to the load, and a part of the wave will get what? Will get reflected back. Understood? So now on the transmission line, so what you are going to have? You are going to have both forward traveling wave as well as what? As well as reflected traveling wave. So the superposition of this forward wave and reflected wave is going to form what? Is going to form the standing wave pattern on the transmission line. So whenever the load is mismatched with respect to transmission line, okay, for the transmission line the characteristic impedance is Z0. If the load impedance is not equivalent to characteristic impedance, then you are going to have both forward traveling wave as well as reflected traveling wave. So the superposition of these two waves is going to form the standing wave pattern, and hence on the transmission line you are going to have the standing wave patterns. Okay, so voltages and currents will looks like what are standing wave voltages and standing wave currents on the transmission line. So it happens whenever ZL is not equivalent to Z0. So if ZL equal to Z0 here, then what will happen? Whatever the wave that is incident at the load, that wave will be completely transmitted to the load, because there is no impedance mismatch if ZL equal to Z0. So under that condition you won't see any reflected wave. Yes or no? So if you are not seeing any reflected wave, then there will be no standing wave pattern on the transmission line. Yes or no? Okay. So if ZL equal to Z0, if ZL is equal to Z0, so under this condition there will be no reflected wave on the transmission line. Right? Okay. Okay, so you are going to have only what? Only forward traveling wave. You are having only forward traveling wave, right? Okay. So that means no reflected wave means you are not going to see standing wave pattern. There will be no standing wave pattern on the transmission line. No standing wave pattern on the transmission line, right? Okay. So now, but in general, we can take the load any value now. So it may not be same as characteristic impedance in general. So in general, load is not equivalent to what? Is not equivalent to Z0. So in that case, on the transmission line, you are going to see what? You are going to see the standing wave pattern. So which means you are going to have forward traveling wave as well as what? As well as reflected traveling wave. So the superposition of these two is going to form what? Is going to form the standing wave pattern on the transmission line. Okay, so what is the standing wave voltage on the transmission line here? So just now we have seen that is the solution for voltage. So that is V of L is equivalent to what? V plus e power gamma L plus what? V minus into e power minus gamma L. So I am not writing e power j omega t term here. So that's why I have not represented here t. But you have to understand that V is a function of what? Both L and t. So here whether you write it or not, here e power j omega t term you have to assume, right? Okay. Okay, but here I am doing the analysis only with respect to length, so I am considering only the spatial variations, right? Okay. Next, similarly, I of L is equivalent to what? Is equivalent to I plus into e power gamma L. So just now we have seen V plus by I plus is equivalent to what? Z naught, and V minus by I minus is equivalent to what? Is equivalent to minus Z naught, right? So here you are going to get I plus into e power gamma L. So where I plus is equal to, I can write it as what? V plus by Z naught, V plus by Z naught into gamma L, and here V minus is equivalent to what here? I minus is equivalent to what? I minus, I can write it as minus of V minus by Z naught. So in place of I minus here, I can write it as what? Minus V minus by Z naught into what? E power minus gamma L. So in this manner, I can represent the solution for what? The solution for I of L on the transmission line. Okay, I have represented both in terms of what? V plus and V minus with the help of what? With the help of this characteristic impedance, right? Okay. Okay, so this represents what? This represents a standing wave voltage, and this represents what? This represents a standing wave current, Okay, so once you are having both forward traveling wave and reflected wave, or that forward traveling wave I am calling it as incident wave, and this I am calling it as reflected wave. So once you see both incident wave as well as reflected wave on the transmission line, the superposition of these two waves is going to form the standing wave pattern, and hence this voltage, this total voltage we call as standing wave voltage, and this total current we call it as what? Standing wave current. Okay, now you can take the ratio of standing wave voltage to standing wave current. So if you take the ratio of standing wave voltage to standing wave current, voltage to current ratio is going to give you what? Impedance, right? So since here V is a function of length and I is also a function of length, right? So the impedance that you are going to get by taking this ratio will also become a function of length, right? So that means as you move along the length of the transmission line, this standing wave voltage to standing wave current ratio is going to change. Okay, so this ratio we are calling it as what here? Input impedance on the transmission line. So we are defining another impedance on the transmission line. So that is nothing but input impedance on the transmission line, which is equivalent to standing wave voltage, that is V of L, to what? To standing wave current, that is I of L. If you take this ratio, okay, so then it is called as what? It is called as, we call it as input impedance seen on the transmission line. So it is a function of what? It is a function of length of the transmission line. Okay, we have already defined one impedance, that is characteristic impedance. Now we are defining another impedance, that is nothing but input impedance. So there is a difference between characteristic impedance and input impedance. So characteristic impedance is defined with respect to traveling wave patterns, yes or no, whereas input impedance is defined with respect to standing wave patterns. Okay, that is the difference here. So whenever you are defining with respect to traveling wave patterns, then V plus by I plus ratio, that is forward traveling wave voltage to traveling wave current ratio, will become independent of length. Okay, so that's why characteristic impedance is independent of length, whereas whenever you are taking standing wave voltage to standing wave current, since this V and I are functions of length, here Z in will also become function of length. So this input impedance is function of what? It is a function of length. Right? Okay. Okay. So here I am not doing any derivation here. What is the expression that you are going to get here is Z naught into Z naught into ZL, Z naught into ZL plus Z naught into tan H gamma L, I think. Yes. Okay, divided by Z naught plus ZL into tan H gamma L. Okay, so this is the expression you are going to get for input impedance seen on the transmission line here. So this is for a lossy transmission line. We are dealing with lossy transmission line. So here gamma is equivalent to what? Gamma is equivalent to alpha plus J beta, alpha plus J beta, right? Okay, and we have determined gamma as a square root of what? R plus J omega L into what? Into Z plus J omega C, right? Okay. Right. So the expression we got for in case of a lossy transmission line, okay, so the expression for gamma is equivalent to square root of R plus J omega L into Z plus J omega C, and the expression for characteristic impedance is square root of what? Square root of R plus J omega L by Z plus J omega C, and the expression for input impedance is Z naught into what? Z naught into ZL plus Z naught into tan H gamma L divided by Z naught plus ZL into tan H gamma L. Okay, so there is one more parameter to be defined here, so that is a reflection coefficient here, reflection coefficient gamma of L. Okay, so reflection coefficient on the transmission line, right? So this reflection coefficient on the transmission line, how we are going to define is so it represents how much part of the incident wave is getting reflected from the load. Okay, so that is called as a reflection coefficient here. How much of the incident wave is getting reflected back. Okay, so what fraction of the incident wave is getting reflected back, so that is given by reflection coefficient on the transmission line. So that is nothing but you have to take the ratio of a reflected wave to what? To incident wave. You have to take the ratio of reflected wave to incident wave. So what is reflected wave here? Reflected wave is nothing but V minus into e power minus gamma L divided by incident wave is V plus into e power gamma L. So that is nothing but you can take it as V minus by V plus into what? E power minus 2 gamma L, right? Okay, now at load here, at load L is equal to what? L is equal to 0. So this is the transmission line, this is the load, right? Okay, we always consider the reference as our load and we'll start moving from load to source, right? So at load L is equal to what? L is equal to 0. So that means at load the reflection coefficient will become what? Gamma of L is equal to 0, which is equal to what? Gamma L. Okay, so gamma L represents what? This L represents a load here, right? So this represents the reflection coefficient at load. So the reflection coefficient at load is nothing but what? V minus by V plus, V minus by V plus. Okay. Okay. So the reflection coefficient at load is nothing but V minus by V plus. So I will give you the formula directly for gamma L and gamma of L. So gamma L, that is the reflection coefficient at load, is we can express this in terms of what? Load impedance and characteristic impedance. So that is you are going to get ZL minus Z0 divided by what? ZL plus Z0, right? So this is the expression for reflection coefficient at load. So in general, this ZL can be a complex quantity and Z0 can also be what? Can also be a complex quantity. So in general, this gamma L is a complex quantity. So if it is a complex quantity, so it is going to have what? Both magnitude as well as what? As well as phase shift. Okay. So this phi L represents the phase shift. This phi L represents phase shift of reflection coefficient at what? At load. So this is the magnitude here. This is the magnitude of reflection coefficient at what? At load, right? Okay. So this is the reflection coefficient at load here. So if you want the reflection coefficient at any location on the transmission line, so that is gamma of L is equivalent to what? Is equivalent to V minus by V plus into e power minus 2 gamma L. So minus 2 into gamma is nothing but alpha plus J beta into L. So this I can represent as V minus by V plus into e power minus 2 alpha L into e power minus J 2 beta L. So just now we have seen that this V minus by V plus is nothing but what? Is nothing but reflection coefficient at load, which is equivalent to what? Magnitude of gamma L into what? E power J phi L. So if you substitute that, what you are going to get? You are going to get the reflection coefficient at any location on the transmission line is equivalent to magnitude of gamma L into e power minus 2 alpha L into e power J of what? E power J of phi L minus what? Minus 2 beta L. So this is the expression for reflection coefficient at any location on the transmission line. Okay. Okay. So this is the reflection coefficient at any location on the transmission line. So reflection coefficient at any location on the transmission line, right? Okay. So if you want at load, what you have to do? You have to just replace L is equal to what? L is equal to 0. So if you put L is equal to 0, then you are going to get the reflection coefficient at load, right? Okay. Okay. So if you observe here, this is the amplitude of the reflection coefficient. So this is the amplitude, right? And this is the phase. Right? So as L goes on increases here, as you move from load to source, this L value is going to increase. So as this L value increases, what happens to this amplitude of reflection coefficient? Amplitude of reflection coefficient is going to decay exponentially as you move from load to source, right? And similarly, if you consider this phase here, okay, here you are having 2 beta L. So as L goes on increases, okay, that means you are moving from load to source. As you move from load to source, this L value goes on increases. As this L value goes on increases, this 2 beta L value is also going to increase, and you are subtracting this 2 beta L from what? From phi L. So that means as you move from load to source, the overall phase of the reflection coefficient is going to what? Is going to decrease. Why it is going to decrease? Because this 2 beta L is getting subtracted from what? Phi L. Right. So as L increases, this 2 beta L value is going to increase. So if you subtract this from phi L, so the overall angle is going to decrease. So that means as you move from load to source, the phase of the reflection coefficient is decreasing, and at the same time the amplitude of the reflection coefficient is also decaying exponentially. Yes or no? Okay. So those are the two conclusions that we can make in case of what? Lossy transmission line, right? Okay, so the amplitude of the reflection coefficient is decaying exponentially, and also the phase of the reflection coefficient is decreasing as you move from load to source, right? Okay. Okay, so here we have represented Z in. So here Z in is a function of what? It is a function of length, whereas Z naught is independent of length, right? Next, we have determined the expression for gamma also. So what is the expression for gamma? Reflection coefficient is equivalent to magnitude of gamma L into e power minus 2 alpha L into e power j of phi L minus 2 beta f. Right, this is the expression for reflection coefficient on the transmission line. So this is the amplitude and this is the phase. Okay, so reflection coefficient at load here, reflection coefficient at load gamma L is equal to magnitude of gamma L into e power j phi L. So R, this is equivalent to what? ZL minus Z naught divided by what? ZL plus Z naught. Okay, so based on this we can whatever may be the question. Okay, so almost all the questions will be based on these parameters only. They may ask for gamma, or they may ask for Z naught, or they may ask for input impedance, or they may ask for reflection coefficient, right? Okay. See, the only one thing here is you have to deal with, in every expression you have to deal with what? You have to deal with complex quantities, right? So whenever you are having a complex number here, whenever you are having some complex number, okay, so you can easily determine its magnitude. But whenever you are determining phase shift, generally the students are going to have some doubts here. Okay, so I will tell you how to determine that phase shift whenever you are dealing with complex numbers. So let us say you are getting a plus jb, right? So then the magnitude you can write directly, that is square root of a square plus b square, and the phase shift is nothing but what? Tan inverse of what? Tan inverse of b by a. So here it is going to be simple. Okay, but if you are having minus a plus jb, okay, then also the magnitude will be same. Then how you have to write the phase? Right, so here generally the students will have some doubts how to express this angle, right? Or if you have minus a minus jb, then how to express the, for this also the magnitude will be same, but you have to express the phase shift. You have to express the phase shift. Phase shift is going to be different, right? So how to deal with the complex numbers? So whenever you are dealing with the complex numbers, you can easily determine the magnitude. You can easily deal with the magnitudes, but where you will get doubt means whenever you are calculating what? Whenever you are calculating the phase shift. Okay, so generally the phase is going to take the range of phase it will be what? Will be 360 degrees, right? So that phase in generally you can consider from 0 to 360. Or if you consider both negative angles as well as positive angles, then in that case you will consider phi is varying from where to where? Minus 80 to what? To plus 180, right? Minus 80 to plus 180, right? So if you consider from minus 180 to plus 180, then you will get the total range of phi, that is 360 degrees. So here I am including both negative angles as well as positive angles. So generally we will consider both negative angles as well as positive angles. So in that case, how to represent the phase of a complex quantity here? So let us consider a complex plane. So this is the real part and this is the imaginary part, right? Okay, okay. So if you are having the complex number as a plus jb, a plus jb, okay, a plus jb, so it is lying in the first quadrant, right? Okay, A is positive, real part is positive, imaginary part is also positive. So in this case, the phase shift will be, we can write tan inverse of what? Magnitude of imaginary part, that is B, magnitude of real part, that is A. Magnitude of imaginary part to magnitude of real part, right? Okay, if the complex number is lying in the second quadrant, so if it is second quadrant, you are going to have what? Negative real part and positive imaginary part, minus A plus ZB. So in this case, how we can represent the phase shift here? Phase shift will be equivalent to 180 minus what? Minus tan inverse of what? Tan inverse of magnitude of B by magnitude of A, right? So that is magnitude of imaginary part by magnitude of real part. So you can write like that here. Okay, so you can write in a generalized manner. So tan inverse of magnitude of imaginary part divided by magnitude of real part. Okay, okay. Next, if the complex number is lying in the third quadrant, so here minus A minus ZB. So in this case, the phase shift, how you are going to, you have to represent here. So the phase shift is nothing but minus of 180 minus tan inverse of what? Minus tan inverse of magnitude of imaginary part divided by what? Magnitude of real part, right? Okay, so this is equivalent to what? This is equivalent to minus 180 plus tan inverse of what? Tan inverse of magnitude of imaginary part to magnitude of real part. So in this manner, you have to represent the angle phi if the complex number is lying in the third quadrant, right? So if the complex quantity is lying in the fourth quadrant here, so let us say if it is in fourth quadrant, real part will be positive, whereas imaginary part will be negative. Okay, so you are going to have A minus JB like this. Okay, so here you have to represent the angle as a simply phi is equal to minus tan inverse of what? Minus tan inverse of magnitude of imaginary part by magnitude of real part. You can follow this one here, right? Okay, okay. So whenever you are dealing with the complex quantities, right? So if the complex number is lying in the first quadrant, then while calculating its phase shift, you just simply take a tan inverse of what? Tan inverse of magnitude of imaginary part to magnitude of real part. Magnitude of imaginary part to real part. That's it. Okay, if it is lying in second quadrant, you can consider the angle as what? 180 minus tan inverse of what? Magnitude of imaginary part to magnitude of real part. So if it is lying in the third quadrant, then you consider the angle as minus 180 plus tan inverse of magnitude of imaginary part by magnitude of real part. So if it is lying in the fourth quadrant, then you can consider it as what? Minus tan inverse of what? Magnitude of imaginary part by magnitude of real part. So here in general, we will consider the angles as both positive as well as what? Negative. So in that case, you can determine the phase of the complex numbers in this manner, right? Okay, okay. So if you understand this one, right, then you can deal with the complex numbers in a very simple manner, right? So here you are going to get some complex quantity. So that complex quantity, you can determine magnitude as well as phase, and for this complex quantity also you can determine magnitude and phase, right? Suppose you get the magnitude as a into e power j phi 1 in the numerator, and in the denominator if you get the magnitude as b into e power j phi 2. So then you can write it as what? Its magnitude will become a by b, and phase shift will become what? E power j of phi 1 minus phi 2, right? You can simplify this one or not, right? E power j means cos of phi 1 minus phi 2 plus j into sin of phi 1 minus phi 2. So finally you are going to get one complex quantity. That's it, right? Okay, so in that manner you can easily solve, or you can easily deal with what? With these complex quantities. So determining magnitude is simple. So if you understand how to determine this phase shift, then you can easily deal with the complex quantities, right? Okay. See, I am not concentrating on the mathematical calculations here, so it is your part. So what I am doing is how you have to analyze the given problems with the help of these concepts. Okay, so those things I am concentrating, right? So this is what is most important here. Okay, okay, right. So here I am taking the break here. So after this I will here I have dealt with lossy transmission line. Okay, so now I am taking break. So after break I will start deal with lossless transmission lines. So once I deal with lossless transmission lines, once I revise those lossless transmission lines, then I will go for waveguides, and after that we will see antennas. So in antennas mainly I am going to uh, uh, teach the topic of antenna arrays, right? Okay, okay. So I am taking break here, break. So the break time will be, now the time is 1:30, so 1:30 to 2:30 here, 1:30 to 2:30 break. Okay, so we'll meet at 2:30 p.m. right? Okay, right. Okay, so I am taking break. So after break we will meet. So we'll meet at 2:30 p.m. Okay, okay. So okay then, take care, bye bye, and thank you for watching. Right, we'll meet again at 2:30 p.m. Hello. Right. So in the morning session, we have started transmission lines, right? Okay. So in transmission lines, we have deal with a lossy transmission line, right? We have deal with lossy transmission line. So we got gamma is equal to square root of j omega mu into sigma plus j omega epsilon, right? And then characteristic impedance z naught equal to square root of r plus j omega l by z plus j omega c, right? And then the input impedance seen on the transmission line, you got z naught into zl plus z naught into tan h gamma l divided by z naught plus zl into tan h gamma l. Okay, and then input impedance expression, characteristic impedance, and then what we got here, reflection coefficient, right? So gamma of L is equivalent to magnitude of gamma L into e power minus 2 alpha L into e power j of phi L minus 2 beta L. So this is the expression for reflection coefficient at any location on the transmission line. Next, we got reflection coefficient at load. Reflection coefficient at load. So that is gamma L is equivalent to magnitude of gamma L into e power j phi L. Okay, and we can represent the same reflection coefficient at load in terms of ZL and Z0 as ZL minus Z0 divided by what? ZL plus Z0, right? Okay. Okay. So now we try to solve some problems here. We try to solve some problems based on this. Right. Okay. Okay. So let us consider this question here. So what they have given is a transmission line. So a transmission line. So what they have given is the propagation constant gamma is equivalent to 2 plus j5 meter inverse. So propagation constant value they have given, and then characteristic impedance value they have given as 50 plus j0, 50 plus j0 ohms at a frequency omega equal to 10 to the power of 6 radian per second, right? So then they are asking to determine the values of L, C, R and Z values. What are the values of L, C, R and Z? So this is what they are asking here, right? Okay. So here, so on this transmission line, what are the parameters they have given? So on the transmission line they have given gamma is equal to 2 plus j5. So 2 means they have given alpha value, 5 means they have given beta value. So since here alpha is not equal to 0, so the line is going to behave as what? The line is going to behave as lossy transmission line. That is confirmed. Okay, it is going to behave as lossy transmission line since alpha is not equal to what? Since alpha is not equal to 0. So this implies that the line is going to behave as lossy transmission line, right? And on this lossy transmission line, they have given Z0 is equivalent to 50 plus J0 here. They have given Z0 is equivalent to 50 plus J0 at a frequency, and this transmission line is operating at a frequency of what? It is operating at a frequency of 10 power 6 radian per second. Right. So then they are asking us to determine L, C, R and Z values. We have to determine L, C, R and Z values, right? Okay, okay. So now see here how we can determine that. See, they have given gamma, right, and they have given Z0. Okay, and the line is what? And the line is a lossy transmission line. Lossy transmission line. So this is what we can confirm, right? Okay, so the expression for gamma in case of lossy transmission line is nothing but what? Root over R plus J omega L into what? Into Z plus J omega C. And what is the expression for characteristic impedance in case of lossy transmission line here? That is Z0 is equal to square root of R plus J omega L divided by what? Divided by Z plus J omega C, right? Okay, Z plus J omega C. Now, now if you multiply this gamma into Z0, if you multiply this gamma into Z0, what you are going to get? If you multiply gamma into Z0, so this root over Z plus J omega C, here root over Z plus J omega C will get cancelled. You are going to get what? You are going to get R plus J omega L, right? Okay, so similarly, if you take a gamma by Z0 here, if you take gamma by Z0, okay, then what you are going to get? So if you take a gamma by Z0, what you are going to get? You are going to get a Z plus what? Z plus J omega C. So this is what you are going to get. So gamma into Z0, you will get a R plus J omega L, right? And gamma by Z0, you will get a equivalent to Z plus J omega C. So here they have given both gamma values as well as what? As well as gamma values as well as what? Z0 value. So gamma value what they have given? 3 plus J5, right? So gamma they have given as a 2 plus J5, right? So gamma is 2 plus J5. So they have given gamma as a 2 plus what? 2 plus J5, right? So this multiplied by Z0. Z0 they have given as Z0 is equivalent to 50 plus J0. 50 plus J0 ohms they have given. So that means Z0 equal to 50 here, right? So Z0 value they have given as 50. So this is equivalent to R plus J omega L. Okay. Now here, what is the real part here? Real part is nothing but 100 plus 5 into 50 is how much here? 250, right? So this is equivalent to R plus J omega L. Now compare the real parts on both sides. You are going to get what? You are going to get R value. So that is R is equal to 100 ohms. You are going to get. Okay. So here in transmission lines, the units of resistance, inductance and capacitance are defined per meter here, are defined as per meter, because this R, L, Z and C doesn't represent the lumped elements, but these are going to represent what? Distributive elements. So that's why the units of this R, L, G and C are nothing but what? Are defined per meter. So that means here the resistance value is ohm per meter, ohm per meter, right? Okay. Next, if you compare the imaginary parts here, so that is omega into L, which is equivalent to what? 250. So they have given omega as 10 to the power of 6 radian per second. So therefore L value is equivalent to what? 250 divided by 10 power 6. So that is you are going to get 250 microhenry. Yes or no? Okay. So this is the value of L. Now similarly, if you take the ratio of gamma by Z0 here. So gamma is nothing but 2 plus J5. So divided by what? Z0 is 50. So this is equivalent to Z plus J omega C. So here also, so 2 by 50 here. So you will get here 2 by 50 plus what? Plus J into 5 by 50. What is 5 by 50? 5 ones 5 times. So 1 by 10, that is 0.1. Okay. So this is equivalent to Z plus J omega C. So compare the real part on both sides. You are going to get Z is equivalent to 2 by 50 mho per meter. 2 by 50 mho per meter. So this is the value of Z, right? Next, if you compare the imaginary parts on both sides, what you are going to get? You are going to get omega into C is equivalent to 0.1. So from here, what is C here? C is equivalent to 0.1 divided by what? So omega is 10 power 6. Okay, so 0.1 divided by 10 power 6. So that is equivalent to 0.1 microfarad per watt per meter. So here for inductor also it is microhenry per watt per meter. So I have told that all the parameters are defined per meter, are defined as per meter. Okay. Okay. So C is equivalent to what? C is equivalent to 0.1 microfarad per meter, whereas L is equivalent to 250 microhenry per meter, and R value is nothing but what? Is nothing but 100 ohm per meter, and here Z value is 2 by 50 and C value is 0.1, right? Okay. So we have determined all the parameters here, that is R value, L value, Z value and C value, right? Okay. This is how we can do. So but in general here if you observe, they have given in this problem, they have given Z0 is equivalent to 50 plus J0 ohms here. Okay, but in general for a lossy transmission line, Z0 equal to what? Square root of R plus J omega L by what? By Z plus J omega C. This is the expression for characteristic impedance, right? Okay, in general. But here, even though they are saying the transmission line as lossy transmission line, sorry, lossy transmission line in the previous problem, okay, but they have given the characteristic impedance as a real quantity. Imaginary term is 0. Okay, so is it possible when this Z0 will become a real quantity here? When this Z0 will become a real quantity? Tell me when it is going to become real quantity. So now that is Z0 is equal to see here. Now what I am doing here is if I take omega L common in the numerator and omega C common in the denominator, so you are going to get omega L by omega C into what? Into R by omega L, right? R by omega L plus J divided by what? Divided by Z by omega C plus J, right? Okay, so here omega will get cancelled. So now if I consider if R by omega L, if I make R by omega L is equivalent to Z by omega C. So here omega will get cancelled. So this implies R by L is equal to what? Z by C. So if I make R by L is equal to Z by C, right? Okay. So if I make R by L is equal to Z by C, then what will happen? This term and this term will get what? Will get cancelled. Yes or no? If I make R by L equal to Z by C, this numerator term, denominator term will get cancelled. So therefore, under this condition, you will get what? Characteristic impedance as what? Square root of L by C. Right. So that means even for a lossy transmission line, you are going to get what? You are going to get the characteristic impedance as a real quantity. Real quantity if and only if. When it is going to happen? Whenever R by L is equal to Z by C. So generally this R by L equal to Z by C is the condition for a distortionless transmission line here. This is the condition for what? Distortionless transmission line. Okay, so if the line is lossy and if the characteristic impedance is becoming a real quantity, then you have to keep in mind that the line is behaving as what? Distortionless line. Only under this condition, a lossy transmission line is going to have real value for the characteristic impedance. Right? Okay. So in general, the characteristic impedance of a lossy transmission line is complex in nature, but under one condition, this characteristic impedance can become a real quantity. So that is whenever R by L equal to Z by C, so the characteristic impedance is becoming a real quantity, and this is the condition for what? Distortionless transmission line. Okay, so that means here, even though the line is lossy transmission line, it is behaving as what? Distortionless transmission line. Right? Okay, so a lossy line can behave as what? Can behave as distortionless transmission line whenever R by L equal to Z by C. Right? Okay. Okay. So for a lossy transmission line, the characteristic impedance will become real for if the line is behaving as what? If the line is behaving as distortionless. Right? Okay. So in the given problem also here, in the given problem also, since they have given the characteristic impedance as 50 plus J0, that is imaginary part is 0, that means Z0 is a real quantity, right? And here alpha is not equal to 0. So that means it is lossy transmission line, but the characteristic impedance is a real quantity, which means they have given the parameters for what? For a distortionless transmission line. That's what you have to understand, right? Okay. Okay, so here the line is going to behave as what? The line is going to behave as a distortionless transmission line. And what is the condition for this one? For this one, the condition is R by L must be equal to what? Z by C. So if you want whatever the values we got here for R, L, G and C. So for R what we got? 100. For L what we got? 250. So what is R by L? Tell me. R by L is equivalent to what? R value is 100. L value is 250 microhenry per meter, that is 10 power minus 6. So here take Z by C here. So Z is nothing but 2 by 50 and C is nothing but what? 0.1 into 10 power minus 6. So this is equivalent to what you are going to get? Tell me. So 2 divided by 5 into 10 power minus 6. 2 divided by 5 into 10 power minus 6. So here 0, 0 will get cancelled. So here 5 2s, 5 5s. So here also what you are getting? 2 divided by 5 into 10 power minus 6. So here also you are getting the same thing or not? Yes or no? So you can conclude that here R by L is becoming same as what? R by L becoming same as Z by C. So that's why here the characteristic impedance of a lossy transmission line has become real quantity. Okay? Okay. So for a lossy transmission line, when its characteristic impedance will become real? Whenever the line is behaving as a distortionless transmission line. So the condition for distortionless transmission line is R by L equal to G by C. Okay? Okay. So here also we can check that here. Since characteristic impedance they have given real quantity, so we have to get R by L equal to Z by C. So the same thing we are getting here. So we have verified that one also, right? Okay. Okay. Right. Right here. So next we'll move on to lossless transmission line. We'll move on to lossless transmission line. So the condition for lossless transmission line is what here? R equal to 0 and Z equal to 0. So this is the condition for a lossless transmission line. So just put R equal to 0 and Z equal to 0 in all the expressions. Then you are going to get the expressions for characteristic impedance, input impedance, reflection coefficient and all those things. Right? Okay? Okay. So what you are going to get? Tell me. So if you put R equal to 0 and Z equal to 0, then what is the expression you are going to get for gamma here? So gamma is equivalent to square root of R plus J omega L into Z plus J omega C. Put R equal to 0 and Z equal to 0. So you are going to get square root of J omega L into J omega C. So take J omega outside the root, then you are going to get J omega root LC. Okay, so if you compare this with alpha plus J beta, so what you are going to get? You are going to get alpha is equal to 0 and beta is equal to what? Beta is equal to omega into what? Root over LC. Right? Okay. So this is for lossless transmission line here. So for a lossless transmission line, there should not be any attenuation. So we are getting alpha equal to 0 and beta is equivalent to what? Beta is equivalent to omega into root over LC. So if you compare with uniform plane waves, that is we have studied electromagnetic waves. Yes or no? So if we compare beta with respect to what? With respect to lossless medium here, with respect to lossless dielectric medium, there we got beta is equivalent to what? Omega into root over mu epsilon. So that means in place of mu here, what you are getting? L, and in place of epsilon here, what you are getting? C. right? And also see here, the units of L in case of transmission lines is nothing but what? Is nothing but Henry per meter, Henry per meter. Okay, and the units of mu is also what? And the units of the units of L is nothing but what? Henry per meter, and the units of capacitance is nothing but what? Farad per meter. So here the units of epsilon is also farad per meter, and the units of mu is also Henry per meter. Okay, so in place of mu and epsilon, what we are getting here? L and C, right? Okay, okay, yeah. Right. Next. Gamma. Next, after this characteristic impedance is equivalent to square root of what? R plus j omega L by z plus j omega C. R equal to 0, z equal to 0. So j omega L by j omega C. J omega will get cancelled. You are going to get what? Z naught equal to square root of L by C. Right? Okay. So this is the expression for a characteristic impedance you are going to get. Right? So it is a purely real quantity for lossless transmission line. Okay, for a lossless transmission line, characteristic impedance is going to be a purely real quantity. So if you compare the intrinsic impedance for a lossless medium, okay, in case of electromagnetic wave propagation, what we got? Eta is equal to square root of mu by epsilon. So in place of mu, what you are having? L, and in place of epsilon, what you are having? C. Okay, like that you can compare here, right? Okay, right. So this is the expression for a characteristic impedance in case of lossless transmission line. So we'll get the same expression of characteristic impedance in case of lossy transmission line also, but when it is going to happen? Whenever that lossy transmission line behaves as what? Distortionless transmission line. Only under that specific condition we'll get the characteristic impedance as square root of L by C in case of lossy transmission line also. If lossy transmission line behaves as a distortionless transmission line, then under that condition also we'll get the same expression for characteristic impedance, right? Okay, okay. Next, what is the expression for input impedance here? Zin of L. Zin of L is equivalent to, you are going to get Z naught into what? Z naught into, here you are having, for lossy transmission line you are having ZL plus Z naught into tan H gamma L. Now here gamma is equivalent to what? Gamma is equivalent to simply here, this is nothing but what? This is nothing but J beta. Okay, so tan H gamma L here, tan H gamma L is equivalent to what? Will become equivalent to tan H of J beta L, tan H of J beta L. Okay, in case of lossless transmission line, gamma will become simply J beta. So tan H of J beta L is nothing but what? Is nothing but J into tan beta L. Is nothing but J into tan beta L. Right? Okay? Okay. So from that we can write in place of tan H gamma L, just replace with J tan beta L. So then you are going to get the expression here as Z naught into ZL plus J Z naught tan beta L divided by what? Divided by Z naught plus J ZL into what? Into tan beta L. So this is the expression you are going to get for the input impedance on the transmission line. Right? Okay. Input impedance seen on the transmission line. Right? Okay. Next, reflection coefficient here. Reflection coefficient seen on the transmission line, that is gamma of L, is equivalent to what? Magnitude of gamma L into e power minus 2 alpha L, but alpha is equal to 0 here. So you are going to get magnitude of gamma L. E power minus 2 alpha L term will become 1 since alpha is equal to 0. Into what? Into e power j of phi L minus what? Phi L minus 2 beta L. So this is the expression for reflection coefficient on the lossless transmission line. So here also the reflection coefficient at load here, at load gamma L reflection coefficient is equivalent to ZL minus Z naught divided by what? ZL minus Z naught by ZL plus Z0. Okay, so since here in case of lossless transmission line, this Z0 is a real quantity. This Z0 is a real quantity, but ZL can be what? But ZL can be a complex quantity. But ZL can be a complex quantity. So even if ZL is complex, in general, this gamma L will become what? Will become a complex quantity. So in general, this gamma L for a lossless transmission line also, it is nothing but what? In general, it is a complex quantity. So which means it is going to have both magnitude as well as phase shift. That is gamma L is equivalent to magnitude of gamma L into what? E power j phi L. Right? Okay? Okay. So what is the only difference here for reflection coefficient in case of lossy medium and lossless medium? In lossy medium, we have observed that the amplitude of the reflection coefficient will decay exponentially as you move from load to source, whereas here the magnitude of this reflection coefficient will remain what? Will remain same throughout the length of the transmission line. So it is not going to change as you move along the transmission line. Yes or no? This magnitude will remain same, right? But the phase value is going to decrease. Either it may be lossy transmission line or lossless transmission line. So as L goes on increases, this 2 beta value is going to increase. So which means this overall phase is going to decrease. So the same thing is going to happen in case of lossy transmission line also. Okay. So in both the cases, the phase is going to decrease as you move from load to source, whereas the magnitude, this magnitude or this amplitude will remain what? Whereas this amplitude will decay exponentially in case of lossy transmission line, whereas in case of lossless transmission line, this will remain same throughout the length of the transmission line. Okay, it is not going to decay, right? Okay, so that is the difference between lossy and lossless, right? Okay. Okay. Right. Okay. So next, so we try to solve some problems based on this input impedance on the transmission line and reflection coefficient on the transmission line. Okay. Okay. So see here. Okay. So here they have given the transmission line like this. Here this is the transmission line and another section of transmission line they have given here, and another section of transmission line. Okay, so this is the question they have given here. So that is they have given here 3 sections of transmission lines here, so which are connected in this manner, right? 3 sections of transmission lines. So here right. So 3 sections of transmission lines they have given, and here they are asking the input impedance at this location, right? So just name this 3 sections of transmission lines here. So here I am naming them as this as a first section of transmission line, this is a second section of transmission line, this is third section of transmission line. Okay, now if you observe here, this is second section and third section of transmission line here. How these two are connected here? 2 and 3. How these two are connected? These two are connected in parallel or not? Yes or no? So 2 and 3 sections of transmission lines are connected in what? Are connected in parallel. Are connected in parallel. Right? Okay. So we can determine the input impedance of this second section. Let us say the input impedance of the second section is Z in 2. Right. So similarly, the input impedance of the third section is Z in 3. Is Z in 3. Okay. Okay. So then, what is the input impedance seen from the first section here? What is the input impedance seen from the first section? So Z in 1 is equivalent to what? Z in 1 is equivalent to what? So Z in 1 is equivalent to, so it is seeing the input impedance here Z in 2, and here it is seeing the input impedance of Z in 3, and these 2 and 3 are connected in what? Are connected in parallel. So this Z in 1 will become equivalent to what? Will become equivalent to Z in 2 parallel to what? Z in 3. So that is the equivalent input impedance that it is going to see. Okay, so here you can represent here Z in equivalent here, Z in equivalent, right? So here at the first section of the transmission line, the input equivalent impedance that is going to see here at this location is nothing but what? Z in 2 parallel to Z in 3. Okay, so Z in equivalent is equivalent to what? Is equivalent to Z in 2 parallel to what? Z in 2 parallel to Z in 3, right? So but what is Z in 2 here? What is Z in 2? Tell me. So what is Z in 2? So you have to determine Z in 2 and Z in 3. Okay, fine. So once you determine this Z in equivalent, so this Z in equivalent is going to act like what? It is going to act like the load for the first section of the transmission line. So I can draw the equivalent model for the above one in this manner. So I am considering the first section, and here I am terminating this first section of transmission line with what? With Z in equivalent. So I can consider this as what? I can treat it as load impedance for the first section of transmission line. So for this one, the characteristic impedance is R0, right? Okay, and this length they have given as what here? Lambda by 8. So they are asking us to determine the input impedance at this location, right? So where this Z in equivalent is nothing but what? Is nothing but Z in 2 parallel to what? Z in 3. Okay, okay, right. So now what is Z in 2 here? What is Z in 2? So here Z in 2 is nothing but the input impedance seen from the second section of the transmission line. So what is the input impedance? See here, the length of this second section is nothing but what? Lambda by 2. So we know that for every lambda by 2, the input impedance is going to get repeated. So hence I can write here Z in 2 is equivalent to what? Z in 2 is equivalent to 2 R0, right? Okay. Next, similarly here Z in 3. What is Z in 3 here? So Z in 3. So here the length of the transmission line is nothing but what? Lambda by 4. So we know that after lambda by 4, the input impedance seen here, will become what? Z in 3 is equivalent to characteristic impedance square divided by load impedance. So that is Z0 square by ZL. Here Z0 value is nothing but R0 and ZL value is nothing but R0 by 2. So that means Z in 3 is equivalent to what? Is equivalent to R0 square divided by what? R0 by 2. Okay. So here this R0 will get cancelled. You are going to get what? 2 times of R0. So this is Z in 3. Okay. So we got Z in 2 value as 2 R0 and Z in 3 value is also what? 2 R0. So what is Z in equivalent then? So Z in equivalent is equivalent to 2 R naught parallel to what? Parallel to 2 R naught. So since both are same resistances in parallel, so what is the equivalent resistance you are going to get? You are going to get simply R naught. Yes or no? So this is Zin equivalent. So this Zin equivalent, we got it as what? R naught. So that means this Zin equivalent is nothing but the load impedance for the first section. Zin is nothing but the load impedance for the first section. So that means this Zin equivalent is equivalent to ZL1, which is equivalent to what? R naught. And the characteristic impedance of this transmission line is also what? Is also R naught only. So here the characteristic impedance of the transmission line is R naught, and we have terminated this transmission line with a load impedance which is equivalent to what? Which is equivalent to R naught. So that means here the load impedance is same as what? Characteristic impedance. So whenever the load impedance same as characteristic impedance, then what is the impedance that you are going to see on the transmission line? You are going to see only the characteristic impedance, because there will be no standing wave pattern at all. Yes or no? So if there is no standing wave pattern, you cannot see any input impedance and all those things. You will see only characteristic impedance. So throughout the transmission line, or if you want, you are having a Zin of L. Zin of L is equal to what? Z naught into ZL plus what? ZL plus JZ0 tan beta L divided by what? Divided by Z naught plus JZL into what? Tan beta L. So you are having this expression or not for input impedance, right? So now here Z naught is R naught, ZL is also what? R naught. So replace ZL with R naught and Z naught also with R naught. So Z naught with R naught and ZL also with R naught. So what will happen? So here this numerator and denominator term will get what? Will get cancelled. So Zin, the input impedance at any location on the transmission line, will be equivalent to what? Will be equivalent to characteristic impedance. Okay, so whenever the load is terminated with the characteristic impedance, then at each and every location on the transmission line, the input impedance will become same as what? Will become same as characteristic impedance. So whether this length may be lambda by 8 or lambda by 4 or lambda by 2 or lambda by 1000 or lambda by 2000, whatever it may be, so the input impedance is not going to depend upon the length. So here at each and every location, whatever may be the length, irrespective of the length, the input impedance will become equivalent to what? Will become equivalent to characteristic impedance, right? Okay. Okay. The input impedance will become equivalent to characteristic impedance, right? Next see here. So next question, they have given the same type of transmission line structure. So that is they have given 3 sections of transmission lines like this. Okay, so they have given 3 sections of transmission lines. Okay, and here they have given the characteristic impedance of this transmission line as 50 ohm. The characteristic impedance of this one is also 50 ohm, and the characteristic impedance of this one also, let us say 50 ohm. Okay, so here this is 100 ohms, and here let us say this is 200 ohms. Okay, so this length they have given as lambda by 4, and this length let us say they have given this also as lambda by 4, right? Okay, okay, and this length let us say lambda by 8, lambda by 8. So what is the reflection coefficient seen at this location? What is the reflection coefficient seen at this location? So this is what they are asking here. So they have given the 3 sections of transmission lines, right? So the length of this section is lambda by 8, the length of this section is lambda by 4, the length of this section is also lambda by 4. So this is second section, so we can give the naming here. So this is first section, let us say, this is second section, and this is third section. So the second section is terminated with a impedance of 100 ohms, the third section is terminated with a impedance of 200 ohms, right? And this is the first section. So they are asking us to determine the reflection coefficient at this location, right? Okay, okay. So we know the expression for a reflection coefficient at any location on the transmission line. So here we are dealing with what? We are dealing with lossless transmission line here. We are dealing with lossless transmission lines. Okay. Okay. So now see here. Now here I can determine the input impedance seen at this location for the second section of transmission line. Similarly, I can determine the input impedance seen for the third section of transmission line. If you observe, this second section and third section of transmission line, both are connected in what? Both are connected in parallel. Yes or no? So that means the equivalent input impedance seen, at this location here. At this location, that is Zin equivalent. Zin equivalent is equivalent to what? Is equal to what? Tell me. So Zin equivalent is equal to Zin2 parallel to what? Parallel to Zin3. Zin2 parallel to Zin3. So this Zin equivalent is going to act like what? It is going to act like the load impedance for this first section. So this is going to act like the load impedance for the first section, which is equivalent to Zin2 parallel to Zin3, right? So what is Zin2 here? Zin2 is the input impedance seen at the second section of the transmission line. So the length of this transmission line is lambda by 4. So Zin2 is equivalent to what? So if the length is lambda by 4, what is the expression for input impedance you are going to get? You are going to get Z0 square by what? By ZL here, right? Okay, so that is Z0 here is nothing but what? 50. So that is 50 into 50 divided by what? ZL. ZL is load impedance, that is 100 ohms. So divided by 100. So here 0, 0, 0, 0 will get cancelled. You are going to get what? 25 ohms. So this is Zin2. Right. Next, similarly Zin3. So Zin3 is equivalent to what? So here, since this length of the transmission line is also what? Lambda by 4. So the input impedance seen for the third section of the transmission line is also nothing but what? Is also nothing but Z0 square by ZL. Okay. So Z0 is same here. So you are going to get 50 into 50 divided by what? 200. Okay, so you are going to get here 50 into 50 divided by what? Divided by 200. So that is 25 by 2, that is 12.5 ohms. 12.5 ohms, right? So this is what you are going to get for Zin3, right? Okay, so ZL1. So ZL1 is equivalent to what? ZL1 is equivalent to Zin2 parallel to Zin3. So that is 25 ohms parallel to what? Parallel to 25 by 2. Okay. Okay. So this is just like a R parallel to R by 2. So if R parallel to R by 2, what is the equivalent impedance you are going to get? That is R square by 2 divided by what? R plus R by 2, that is 3R by 2, 2 will get cancelled, RR will get cancelled, you are going to get R by 3. So in place of R, what you are having? 25. Okay. So ZL1 you are going to get what? ZL1 you are going to get 25 by 3. Yes or no? Okay. Okay. So the load impedance value you are going to get 25 by 3. by 3 ohms. Right? Okay. Right. So the input impedance seen here is going to act like what? Load impedance for this first section. So I can draw the equivalent model of that transmission line, that is I can take the first section. The equivalent input impedance seen here is nothing but what? Is nothing but the load impedance for this first section, and the load impedance value for the first section is nothing but what? Is nothing but 25 by 3 ohms. 25 by 3 ohms. Right? Okay. So this is the load impedance here. Right. So and the characteristic impedance of this one is 50 ohm, and this length they have given as lambda by 8. So they are asking the reflection coefficient at this input. What is the reflection coefficient at this input? Right. So this is the here. If you know the reflection coefficient at the load here, at the load, then you can determine the reflection coefficient at any location on the transmission line. Yes or no? Okay. So now here gamma in gamma in is equivalent to what? Is nothing but the reflection coefficient at a distance L is equal to what? At L is equal to lambda by 8. At L is equal to lambda by 8. So this is what you have to determine. Okay. So we know that gamma of L here, gamma of L is equivalent to what? Is equivalent to magnitude of gamma L into what? E power j of phi L minus 2 beta L. So this one I can represent as what here? Magnitude of gamma L into e power j phi L is nothing but the reflection coefficient at what? At load. So that I can represent as gamma L into what? Into e power minus j 2 beta L, where gamma L is nothing but magnitude of gamma L into e power j phi L. Okay. Okay. So this gamma L is nothing but what? We know that this gamma L is nothing but ZL minus Z0 divided by what? ZL plus Z0. Okay. So what is ZL here? So here ZL is nothing but 25 by 3 and Z0 is nothing but 50 ohms. Okay. So substitute that, what you are going to get? 25 by 3 minus 50 divided by what? Divided by 25 by 3 plus what? Plus 50. Right. So that is gamma L. So that is, you are going to get 25 minus 75. 25 minus 75 is minus 50 divided by what? Divided by 25, sorry, not 3 into 50. 3 into 50 is 150 na? Okay. So 25 minus 150. 25 minus 150 is minus 125 divided by 3. And here 25 plus 150, so that is 175 divided by 3. So 3 will get cancelled, right? Okay. So you are going to get 5 25s are, right? And here 5 3s are 15, 5 5s are 25. Okay. And again 5 5s are and 5 7s are. What you are going to get? Minus 5 by 7. Minus 5 by 7. So this is gamma L value here, right? Okay. So this value we got, right? So gamma L value we got it as what? We got it as minus 5 by 7, right? Okay. So therefore gamma in is equivalent to gamma of L is equal to lambda by 8 is equivalent to what? Is equivalent to gamma L into what? Gamma L into e power minus j 2 beta L. So beta I am writing as 2 pi by lambda into L value is nothing but what? Lambda by 8. Lambda by 8. So we want the reflection coefficient at L is equal to lambda by 8. So wherever you are having L, there I am replacing with lambda by 8. Okay. Okay. So this gamma L is nothing but the reflection coefficient at load. So this value we got it as minus 5 by 7. Minus 5 by 7. Okay. Okay. Now if you simplify this here, lambda will get cancelled, and here 2 1s 2 4s, and here 2 1s 2 2s. Okay. So you are going to get minus 5 by 7 into what? Into e power minus j 5 by 2. Okay. So this is the reflection coefficient at the input, that is gamma of L is equal to what? L is equal to lambda by 8. Okay. So what is e power minus j pi by 2 here? So this is nothing but cos pi by 2 minus j sin pi by 2. So cos pi by 2 is plus 1 minus j sin pi by 2 is nothing but what? Is nothing but minus j. Yes or no? Minus j sin pi by 2. Sin pi by 2 is 1. So you are going to get minus j. So minus j into minus 1 will become plus j. So therefore gamma of L equal to lambda by 8. So that is gamma in the reflection coefficient at the input is equivalent to what? Is equivalent to j into 5 by 7. J into 5 by 7. So this is how you have to determine the reflection coefficient at any location on the transmission line. So you must aware of the reflection coefficient at any location on the transmission line, and also the reflection coefficient at load. Okay, you have to understand this difference here, right? Okay. So generally students will get confused between the reflection coefficient at load and the reflection coefficient at any location on the transmission line. So both are different, right? Okay. Okay. Next here, next. Okay, so next we try to solve a problem based on voltage standing wave ratio, right? Okay. Okay, so here they have given a lossless transmission line. They have given a lossless transmission line. A lossless transmission line they have given, right? Okay. Okay, or we can solve this problem here. So they have given a transmission line, right? So the load impedance of the transmission line, it is terminated with some load. So the load impedance of the transmission line they have given as R plus jx. Okay, so where R they have given as a 30. Okay, ZL they have given as 30 plus jx, 30 plus jx ohms, right? Okay, and the characteristic impedance of this transmission line they have given as 50 ohms. They have given as 50 ohms, right? Okay, and this length of the transmission line they have given as lambda by 8, and they are asking us they are saying that okay, so if the input impedance seen here is real quantity, is real, if the input impedance seen here is real, then what is the value of this reactance, that is x. Okay, so this is what they are asking the question. So what they have given? They have given a lossless transmission line. So this is, sorry, not lossless, lossless, right? So they have given some lossless transmission line. Okay, so this is the lossless transmission line. Its length is how much here? Lambda by 8. So it is terminated with some load impedance whose value is equivalent to 30 plus what? 30 plus jx ohms, and the characteristic impedance of the transmission line is how much here? 50 ohms, right? So if the input impedance seen for this transmission line is a real quantity, then what must be the value of this reactance? Then what must be the value of this reactance? So that is the question they are asking here, right? Okay, okay. So now see here. Now see here. So we know the expression for a input impedance seen on the transmission line. So that is Zin of L is equivalent to what? Z0 into ZL plus JZ0, ZL plus JZ0 tan beta L divided by what? Divided by Z0 plus JZL into what? Into tan beta L, tan beta L, right? Okay, okay. So now see here. Now here the length of the transmission line, is lambda by 8. Okay, so whenever L is equal to lambda by 8 here, whenever L is equal to lambda by 8, what is beta L? Beta L is nothing but 2 pi by lambda into what? Into lambda by 8, which is nothing but what? Lambda by 4. Sorry, not lambda by 4, pi by 4. Okay, so it will be pi by 4. Yes or no? So here 2 ones, here 2 fours, lambda lambda will get cancelled. You are going to get pi by 4. So beta L value is pi by 4. So therefore tan beta L is equivalent to what? Is equivalent to tan pi by 4, which is equivalent to 1. So wherever you are having tan beta L, they are replaced with 1 here. They are replaced with 1. For L is equal to what? For L is equal to lambda by 8. Right? Okay, so therefore you are going to get Z in of L is equal to lambda by 8 is equivalent to what? Is equivalent to Z naught into ZL plus Z Z naught divided by what? Divided by Z naught plus Z ZL. So tan function will become 1 in the numerator and denominator. The tan function will become 1. Okay, so this is the expression we are going to get, and they are saying that this must be what? This is the input impedance observed is a real quantity. It is a real quantity they have given. Okay, if it is real quantity means the imaginary part of this one must be equivalent to what? Must be equivalent to 0. Here you are having, this is complex quantity, yes or no? So which means here you are going to have a real part plus what? Plus imaginary part. Okay, so you are going to have real part plus what? Plus imaginary part. So let us say the real part is nothing but so you are going to have real part plus what? Plus imaginary part. Okay, okay. So since this input impedance must be a real quantity, which implies that this imaginary term must go to what? Must become 0. Right? Okay, so try to determine this expression here. So you are going to get complex quantity. So in that complex quantity, you have to equate imaginary part is equal to 0. Then you can get the value of what? They are asking the value of what? They are asking the value of this x. Right? Okay, okay. So now see here. So what you are going to get? So what is ZL here? What is ZL in the question they have given? So ZL is nothing but 30 plus what? 30 plus jx. Okay, or you can write r plus jx. You can replace r with 30 later. Okay, so here r plus jx you are going to get, and z naught is how much here? Z naught what they have given? Z naught is 50 ohm, right? Okay, so Z naught is 50. So here Z naught is 50 and ZL is nothing but R plus JX. Okay, so if you do this, what you are going to get? If you substitute this, what you are going to get? So Z naught is 50, right? Okay, so you are going to get 50 into what? Into R plus JX plus what? J50. So that is real part will become what? Real part is nothing but okay, real part is nothing but 50 plus what? Imaginary part is nothing but j into x plus what? X plus 50, right? Wait. Sorry. Okay. 50 into r plus j into x plus 50 divided by what? Divided by here 50 plus j into r j square minus, so 50 minus x, so 50 minus x plus j into 50. So this is what you are going to get here, correct na? So put z naught equal to 50, zl equal to r plus jx. So you are going to get 50 minus x, that is the real part, and plus j into jx. So that is j into jx. Wait. 50 j into jx. J into jx is minus x, so that is 50 minus x. Okay, so the imaginary part is nothing but j into what? J into r, so that is j into 50. Okay, correct here. So this is the input impedance that you are getting, right? Okay. So now if you do, we want real part separately, we want real part separately and imaginary part separately. Then you have to make imaginary part equal to 0. So that is how you can get real part and imaginary part separately here. So that is you can what I have done here. Okay, so here in place of here r, right? Here r, right? Okay, so this into 50 minus x, right, minus j r divided by what? Divided by 50 minus x minus j r. I am multiplying and dividing with 50 minus x, right? 50 minus x minus j r by 50 minus x minus j r. So if you do this, so consider only imaginary part of this one here. What is the imaginary part of this one? Because you have to make a imaginary part is equivalent to 0. So consider only imaginary part. Okay. So how you can do that? See here in the denominator, what you are going to have? You are going to have 50 minus x whole square plus what? Plus r square. This is the denominator you are going to get. So in the numerator, you are going to get r into what? R into 50 minus x. R into 50 minus x and then plus j into x plus 50 minus j into r. So that is plus r into what? Plus r into x plus 50, right? Okay. Next plus j into what? J into x plus 50 into what? Into 50 minus x. 50 minus x, right? 50 minus x and then minus j r into r, that is r square. Okay. So into minus what? Minus r square. So this is what you are going to get here. Okay. So this is the imaginary part and this is the real part. So you have to make imaginary part is equal to 0. So imaginary part, if you consider only imaginary part, what you are going to get? 50 plus x into what? Into 50 minus x minus what? Minus r square. So this must be equivalent to what? This must be equivalent to 0, right? Okay. So what you are going to get? 50 square minus x square is equivalent to r square, right? So x square is equivalent to 50 square minus what? Minus r square. So that is 50 square minus what? R value is how much here? R value is 30. Yes or no? So 30 square. So 50 square minus 30 square. Yeah. So x is equivalent to square root of 50 square minus what? Minus 30 square. So what you are going to get? 50 square minus 30 square. So I think you will get 1600. Okay. So this is equivalent to square root of what? 1600, which is equivalent to what? 40 ohms, right? Okay. So this is the value of reactance here. So that is x value is equivalent to what? X value is equivalent to 40 ohms. This is the value of reactance that you are going to get, right? Okay. Next year. So next, let us take one more problem. So this problem is based on quarter wave transformer technique here. Quarter wave transformer technique. Okay. So let us write that question. A transmission line with a characteristic impedance Z0 is equivalent to 100 ohms. Characteristic impedance Z0 equal to 100 ohms is used to match Z0 equal to 100 ohms is used to match a 50 ohm section, a 50 ohm section to a 200 ohm section. Okay, a transmission line whose characteristic impedance is 100 ohms is used to match a 50 ohm section to a 200 ohm section, right? So they have given, if the matching is to be done, if the matching is to be done, both at 429 megahertz, and 1 gigahertz, then the length of the transmission line, the length of the transmission line, can be approximately okay. So they have given the options 82.5 centimeters, option B 1.05 meters, option C 1.58 meters, option D 1.75 meters, right? So this is the question they have given here, right? Okay. Right. So what they have given, a transmission line whose characteristic impedance is 100 ohms is used to match a 50 ohm section to what? To a 200 ohm section. So a transmission line whose characteristic impedance is 100 ohms is used to match a 50 ohm section to a 200 ohm section. If the matching is to be done both at what? Both at 429 megahertz and 1 gigahertz, then the length of what? Then the length of the transmission line can be approximately. So this is the question they are asking here. Okay. So a transmission line whose characteristic impedance is 100 ohms is used to match a 50 ohm section to a 200 ohm section, right? So which means here you are having a transmission line section, right? So its characteristic impedance is 50 ohms, right? Okay. So this transmission line is used to match what? To match a 100 ohm section to 200 ohm section, is used to match sorry, Z naught equal to 100 ohms here is used to match. Okay, so that means here this Z naught value is not 50, it is 100. Okay, so this value is 100 they have given. So Z naught equal to 100 ohms is used to match a 50 ohm section, to a 200 ohm section. Yes or no? Is used to match a 50 ohm section to a 200 ohm section. So here, let us say here the characteristic impedance is a 50 ohm section to what? It is used to match a 200 ohm section. Is used to match a 200 ohm section. Okay, so let us say this is a Z0 1 and let us say this is a Z0 2, right? Okay, so they have used a transmission line section. This is the transmission line section. This is the transmission line section that is used to match 50 ohm section to what? 50 ohm section to 200 ohm section here. 50 ohm section to 200 ohm section. Now if you observe here, for this transmission line, Z0 is equivalent to what? Z0 is equivalent to square root of what? Square root of, I can write it as 50 into what? 50 into 200. Okay, that is the impedance seen on this side is 50 ohms and the impedance seen on this side is how much? 200 ohms, which is equivalent to what? Which is equivalent to 100 ohms. So that means the characteristic impedance of this section of transmission line which is used for matching, its characteristic impedance is equivalent to the impedance seen on this side, that is 50 ohms multiplied by the impedance seen on this side under root. Okay, so that means the impedance of this one is just like what here? ZQ is equivalent to square root of what? Square root of the impedance seen on this side is Z in 1 and the impedance seen on this side, let us say Z in 2. Understood? The impedance seen here is Z in 2, that is 200 ohms. The impedance seen on this side here is Z in 1, that is 50 ohms. Okay, so right? Okay, so here since the characteristic impedance of this transmission line is equivalent to square root of impedance seen on this side multiplied by impedance seen on this side, we can decide that this transmission line is nothing but what? This transmission line is nothing but quarter wave transformer. It is going to act like a quarter wave transformer. So what is the length of this quarter wave transformer here? What is the length of this quarter wave transformer? The length of the quarter wave transformer can be what? It can be odd multiples of what? So it can be odd multiples of lambda by 4. So this is the length of this quarter wave transformer. Okay, so they are asking what must be the length of this quarter wave transformer such that this quarter wave transformer has to provide the matching at two frequencies. So that is at f1 is equivalent to 429 megahertz and at f2 is equivalent to 1 gigahertz, right? 1 gigahertz. So at both these frequencies, if this quarter wave transformer has to provide the matching, then what must be the length you have to take? Okay, so here the length of the quarter wave transformer is nothing but what? Odd multiples of lambda by 4. So what length you have to choose such that it has to provide the matching at both of these frequencies. Okay, so you have to determine the length at which this quarter wave transformer is going to provide the matching for both the frequencies, right? Okay. So now first let us determine the lengths. Lengths that are First let us try to determine the length of the quarter wave transformer that is going to provide the matching at frequency f1 here. First what we will do is we will try to determine the lengths of the quarter wave transformer which is going to provide the matching at 421 megahertz. Similarly, we try to determine the lengths of quarter wave transformer which is going to provide what? Which is going to provide the matching at frequency f2. Right? Then if you determine the common lengths here, in these two, Okay, then you are going to get the lengths that are going to provide the matching at both the frequencies. First, what we will determine? We will determine the lengths, okay, lengths of the quarter wave transformer that are going to provide the matching for this frequency. Similarly, we try to determine the lengths of the quarter wave transformer which are going to provide the matching at 1 gigahertz frequency. Then if you determine the common lengths of these two, then you are going to get the lengths of the quarter wave transformer that is going to provide the matching for both the frequencies, right? Okay, so that is the procedure we have to follow here. So let us take at frequency f1 is equivalent to what? F1 is equivalent to 429 megahertz. So at this frequency, what are the lengths that are possible here? So the lengths that are possible at frequency f1 is equivalent to what? Is equivalent to 2m plus 1 into what? Into lambda 1 by 4, where lambda 1 is the wavelength at frequency f1, right? Okay, so where lambda 1 is equivalent to what? Is equivalent to c by f1. Okay, so this is equivalent to 3 into what? C is nothing but 3 into 10 to the power of 10 centimeters per second divided by f1 is how much here? 429 megahertz. That is 429 into 10 power 6. So this is equivalent to. So what is lambda 1 value you are going to get? Tell me, what is lambda 1 value? So that is 3 divided by 429. So that is 10 power minus 3. So into 10, so 10 power 7, so 10, so you will get 70 centimeters here. Approximately you will get 70 centimeters. Approximately you will get 70 centimeters as lambda 1. So what are the common lengths you are going to get? Common lengths at frequency what are the lengths that you are going to get at frequency f1 here? The lengths of the quarter wave transformer at frequency f1 is nothing but what? Odd multiples of lambda 1 by 4, where lambda 1 is nothing but 70 centimeters. Here m is equal to what? M is equal to 0, 1, 2, 3 and so on, right? Okay, so substitute m is equal to 0, what you are going to get? Lambda 1 by 4. So lambda 1 by 4 is nothing but what? So lambda 1 by 4. Next, what is the other length? Next is 3 lambda 1 by 4. Next, you are going to get 5 lambda 1 by 4. Next, 7 lambda 1 by 4 and so on. So these are the lengths of the quarter wave transformer that are going to provide the matching at frequency what? At frequency f1. So what are these values here? So these values are 70 by 4 centimeters, and this is 3 into 70 by 4 centimeters and 5 into 70 by 4 centimeters, comma 7 into 70 by 4 centimeters and so on. Okay, so these are the values you are going to get. So if you do this, what you are going to get? Tell me. So what is 70 by 4 here? So 70 by 4 is nothing but 70 by 4 is nothing but 17.5 here. 70 by 4 is nothing but 17.5. Okay. Okay. So you are going to get here 17.5 centimeters. So this multiplied by 3 is 52.5 centimeters. Next, 17.5 multiplied by 5 is 87.5 centimeters, and 17.5 multiplied by 7 is 122.5 centimeters and so on. Okay, so these are the common lengths here. These are the lengths of the quarter wave transformer that are going to provide the matching at frequency what? At frequency f1. At frequency f1. Okay, so these are the lengths. So similarly, you have to determine the lengths of the quarter wave transformer that are going to provide the matching at a frequency of what? At a frequency f2 is equivalent to 1 gigahertz. So at this frequency, what are the lengths of the quarter wave transformer here? So the lengths of the quarter wave transformer must be equal to what? Lambda 2 by 4, comma 3 lambda 2 by 4, comma 5 lambda 2 by 4, comma 7 lambda 2 by 4 and so on. So odd multiples of lambda 2 by 4. They are going to provide the matching at frequency f2. Yes or no? Okay, so at frequency f2, what is lambda 2 here? Lambda 2 is equivalent to c by f2, which is equivalent to 3 into 10 to the power of 10 centimeters per second divided by frequency is 1 gigahertz, that is 1 into 10 to the power of 9. Okay, okay. So if you do this, what you are going to get? You are going to get 30 centimeters here, 30 centimeters. So this is per second or second inverse, right? Okay, 30 centimeters. So that is lambda 2. So now what are the lengths of the quarter wave transformer that is going to provide the matching at frequency f2 is equivalent to lambda 2 by 4. So that is 30 by 4 here. So what is the value of 30 by 4? So 30 by 4 is equivalent to what? 30 divided by 4 is equivalent to 7.5. Okay, so you are going to get here 7.5 centimeters, comma 3 into 7.5. 3 into 7.5 is 22.5 centimeters, and then 7.5 into 5 is 37.5 centimeters, and then 7 into 7.5 is 52 point 52.5 centimeters. So if I take a next length here, that is 9 lambda 2 by 4. So if you take 9 lambda 2 by 4, what you are going to get? 9 into 7.5. So that is 67.5 centimeters, and so on, yeah, and so on. Right? Okay, and so on. So these are the lengths of the quarter wave transformer that are going to provide the matching at what? At frequency f2. So we have determined the lengths that are going to provide the matching at a frequency of what? At frequency f1, and we have determined the lengths that are going to provide the matching at frequencies of what? At frequency f2, right? Okay, 7.5 into 3, 30 by 4, 30 by 4, 7.5, okay. Right here. Okay, so now you want the lengths of the quarter wave transformer. You want the lengths of the quarter wave transformer that is going to provide the matching at frequency f1 and also at frequency f2. Okay, so that means you want to determine the common lengths of what? Common lengths of LF1 and what? LF2. You want to determine the common lengths of LF1 and LF2. Okay, how we can determine the common lengths here? See, for LF1 here, that means at frequency f1, what we have determined? We have determined lambda 1, which is equivalent to what? C by f1. So from here we can determine the lengths at frequency what? At frequency f1. So the lengths of the quarter wave transformer at frequency f1. So similarly at frequency f2, what we have done? We have determined lambda 2, which is equivalent to C by f2. So from here we have determined the lengths of quarter wave transformer that is going to provide the matching at frequency f2. Right? Okay. Now we want the common lengths of this LF1 and LF2. So if you want to determine the common lengths, how you can determine here? If you determine the common wavelength here of these two, then you can determine the common lengths or not. Yes or no? So LF1 is nothing but what? Lambda 1 by 4, comma 3 lambda 1 by 4, comma 5 lambda 1 by 4, and so on. LF2 is nothing but what? Lambda 2 by 4, comma 3 lambda 2 by 4, comma 5 lambda 2 by 4, comma, and so on. Right? So if you determine the common lengths here, so that means you want to determine the lengths of the quarter wave transformer that is going to provide the matching for both what? For both f1 and f2. for F1 and F2. So that means you have to determine the common wavelength of lambda 1 and lambda 2 here. So we got this lambda 1 as 70 centimeters and this lambda 2 as 30 centimeters. Yes or no? So what is the common wavelength here? So lambda common, what you are going to get is nothing but LCM of what? LCM of lambda 1 and lambda 2. So if you take the LCM of lambda 1 and lambda 2, that is 70 and 30. So what is the LCM you are going to get? You are going to get 210 centimeters. Yes or no? Now in this case, what are the lengths of the quarter wave transformer that is going to provide the matching at both F1 and F2 here? So that is nothing but what? L, which is going to provide the matching at both frequencies F1 and F2 is equivalent to, I can write it as what? L common, that is the common lengths at F1 and F2. Okay, so which is equivalent to 2m plus 1 into what? Lambda common divided by what? Divided by 4. Right? Okay, divided by 4. Right. So which is equivalent to what? Which is equivalent to lambda common divided by what? 4 comma 3 lambda common divided by 4 comma 5 lambda common divided by 4 and so on. So these are the lengths of the quarter wave transformer that are going to provide the matching at both the frequencies F1 and F2. If suppose they have added another frequency here, let us say they have added what are the lengths that are going to provide matching at frequency F1, F2 and F3, then you have to determine the LCM of lambda 1, lambda 2 and lambda 3. Right? Then the lengths will become what? The lengths will become 2m plus 1 into lambda common, where this lambda common is the LCM of lambda 1 and lambda 2. Okay? Okay. Lambda common is nothing but LCM of lambda 1 and lambda 2. If they have given more than 2 frequencies, then you have to determine the LCM of those wavelengths here. Right? Okay? Okay. So lambda common is how much here? 210. So if you determine that, what you are going to get? So you are going to get here 210 divided by 4. 210 divided by 4 centimeters, comma 3 into 210. Okay. So what is 210 divided by 4 here? 210 divided by 4 is 52.5 centimeters. So 210 divided by 4 is equivalent to 52.5 here. 52.5. So okay, so 52.5 here, 210 divided by 4 is 52.5. So I am writing directly here. So this lambda common is nothing but 210, right? So 210 divided by 4 is 52.5. So the first length is 52.5 centimeters and the second common length is 3 times of this. So 3 times of this is 157.5 centimeters and the third one is 5 times of 52.5. So that is 5 into 52.5. So that is 262.5 centimeters and so on and so on. Okay. So if I write it in meters here, what you are going to get? 0.525 meters, or you can represent in meters also. So then 1.575 meters, comma 2.625 meters and so on. So these are the lengths. That are going to provide the matching at frequencies both F1 and F2. Okay. So we can call them as a common lengths here. Common lengths of F1 and F2. Okay. So these are the lengths of the quarter wave transformer that are going to provide the matching at what? At both the frequencies F1 and F2. Right? Okay. Okay. So now see here. So see the answer here. Answer what they have given. In option A they have given 82.5 centimeters. In option B they have given 1.05 meters. right? Option C they have given 1.58 meters, option D they have given 1.75 meters. So which one is correct here? Tell me, which one is correct? What we got? We got 0.525 meters, 1.575 meters. So this is approximately, you can write it as 1.57 or 58 meters. Okay. Okay. So if you observe here, we are having this length here. So that is 1.58. Okay. So 1.58 or 1.575 something we got. Okay. So whatever the answer we got, that is nearer to this option C. Right. So that is option C, 1.58 meters is the right answer for this question. Right. Okay. Right. So these are some different types of problems in the transmission lines here. Okay. So next, similarly, we will see some different types of problems in case of what? In case of rectangular waveguides and in case of antennas, antenna arrays. Okay. Antenna arrays. Right. So I am taking break here now. So taking break. So after break, we will see some. I will discuss some few problems of rectangular waveguides and antenna arrays. Right? Okay. So the break time now here. The time is 4:10 here. So 5 minutes break. 5 minutes break. So we'll meet at 4:15 p.m. Okay. We'll meet at 4:15 p.m. 5 minutes break. Hi everyone, so welcome back. So today I think you are having another session on networks, yes or no? Right now in global channel there is a live session going on for network theory, right? Okay, from 4 p.m. So what I will do is I will continue these two topics here. I will continue these two topics, that is rectangular waveguides and antenna arrays. I will take these two topics tomorrow. Okay, so tomorrow same at the same timing, so that is at 10 a.m. 10 a.m. I will continue this marathon session. So I will complete tomorrow waveguides and arrays here, waveguides and antenna arrays. Okay, okay. So okay then, I am ending up the session for today. So tomorrow we will meet exactly at 10 a.m. So tomorrow I am going to start waveguides and antenna arrays, right? Okay, okay. So we'll meet tomorrow here. So until then, take care, bye bye, and thank you for watching.